So deep learning is a technique used in artificial intelligence to improve the overall uh, to be able to learn highly complex tasks. And how does deep learning achieve is, so basically everything we are trying to do when it comes to computers is manipulating numbers. At the end of the day, we are just doing some kind of basic operations inside the number, that is plus, minus, divide, add, and all of those operations add up to make a new thing. For example, when we are trying to basically when we are trying to make a basic program, for example, a calculator or something even more basic like a word program. If, for example, you are making a text program, you want a text editor like MS Word. So what you have to do for that, you would have to symbolize every keyboard character you press with the help of some numbers that you call the ASCII code, and then you use that code to interpret those and make the screen display pixels that are also numbers between 0 to 255 in 3 different channels. And that is what you are trying to do whenever it comes to, so the basic understanding is, whenever we are working with computers, you are doing some kind of mathematical operations inside the computers to make them do something. So to work with computers, all you have to do is, whatever data you try to work with, you have to convert it into numbers. You have to make some way so that you can convert them to numbers. Now, what does deep learning, where does deep learning come into all of this? So, okay, basically the previous methods that we used to use in the past to create intelligent machines, or we can say machines that can take actions, that can give a suggestion based on some inputs, or give a particular output. For example, a basic bacteria detection machine that was made, those were based on rules, those were based on heuristic rules, man-made rules. Now these man-made rules work great, they are amazing, we have tested them out, but they only work great for subjects that have been tested out, that have a theory behind them. For example, when we are trying to make rules for stuff like, when it comes to stuff um, like again bacteria detection, so what we used to do, we have a big medical book that has a lot of rules that helps a doctor devise what kind of bacteria is the most probable. And we implement the same rule book, the book that is defined in that medical journal, and then we write that as a program, and the program takes decisions with the help of a lot of if else statements, conditional statement, loops, checking, and all of that stuff. Now this worked great, but when it comes to tasks where humans don't really have theory about, you don't teach a child to learn what is an apple and an orange with the help of a theory. You have no book for it that defines an apple, that defines an orange. There are no particular rule book for that. So when it comes to instances like that, our rule based theory really started to give off. Now, to improve on this, we came with an idea of neural networks. Neural networks are loosely inspired from brain. Now, I will not say completely inspired from brain, because we don't know how brain works. If we would have known that, that would have been very essential for the field, but we don't know that, obviously. So instead, what we did was a very basic abstraction of brain, where we said, okay, there are multiple neurons, there is a kind of a swarm intelligence thing going on. So what we can do is, neurons transmit a signal from each other. So what we can do, we can make neurons, we can make different neurons that are just matrices. At the end of the day, they are just like they are just different points in the matrix. And what we do, we pass an input, we pass it through that matrix of neurons. Now those neurons have different weights and different activations, and these weights and activations converts the initial matrix into a different matrix, and we somehow introduce this, whatever the output is, that is compared to what we actually want to output, what is the real value. And this loss helps us train the middle network, the matrix that is in the middle, and we use that training, we use that loss, that loss function is back propagated. Now how does back propagation works, how does forward propagation works? Okay, a basic idea, not going into too much theoretical depth into these basic concepts, but on a basic note, what forward propagation does is, when you're forward propagating through something, what you're doing is, there is a matrix, input matrix, you are multiplying it through a matrix of weights. This gets converted to a output matrix, right? That can be even a scalar, output scalar, but that can also be considered a one by one matrix. So I'm just gonna represent everything with matrices for now. And That is what you are doing basically when you're forward propagating. Now in back propagation, what you do is once you have calculated the loss, the difference between what your neural network uh, predicted when it was weights were randomly initialized, uh, when it is compared to a loss that we actually to the output that we really wanted for that input, right? So that is compared and that gives us the loss, and this loss function is used to train the weights by back propagation. Now how does back propagation works? Okay, let me take out a graph for that. Gradient descent. Now the main thing about machine learning was that while other methods, we have to write a program and give an input and we got an output. But machine learning introduces the concept that we only need to give the machine the input and the output, and machine will figure out the rules, the middle, the matrix itself. So as humans, we see there is a big difference between humans and machines, and that's why super intelligence is such a big concept and we need it, because humans think intuitively. Our brain works in an intuitive and abstract sense. We make sense of things. We don't compute things. When I look at a substance, when I look at an object, I don't compute things that it is this object. I have an intuitive feeling for it. I just see it and I know somehow. That's how the brain works. There are hormones, there are different chemicals that are going other places, there are electrical impulses, and all of that action causes us to interpret something like that in that form. But when it comes to machines, machines have to compute everything. Now this is a big misalignment between humans and machines. We can't make that middle matrix by ourselves because we don't do these operations like this. These operations are in a sense very high level for us. We don't understand how we do it, we just do it. That's how we are made. Now this abstraction is not possible with machines. Machines have to know the perfect computation that they have to commit to learn something. That's why we need the concept of web propagation and automatic learning from the loss function. We need something, some kind of mechanism that can provide that, so that these machines can actually learn these bits. Because as humans, we can't input it because our brain doesn't work the same way. Now again, coming back to gradient descent, what it does is, for example, you have to find the minimum of this value, right? I'm talking about basic machine learning right now. So what you have to do, you have to find the minima of this graph. For example, this graph represents our loss function. So when the graph represents our loss function and we have to find the minima, the points, the matrices where this graph loss function graph is reaching its minima, what we do, for example, at a random initial setting, when the weights were initially randomized, this is where the point where we started. Now what we do, we calculate the loss function and we see what the loss is. Now we calculate partial derivatives of each weight with respect to that loss, and we try to move in the direction where the loss is getting minimized. Okay, so whatever that gradient is, that gradient gives us the direction of where the loss function is. So for example, this is represented here, this gradient. So when I calculate the gradient of this weight with respect to this loss, this came out to be my slope. Now what I'll do is, this is the gradient, so I'll move in the opposite direction because that will lead me to this base case where the loss is minimum, and I'll keep going towards the direction at each iteration, and I'll slowly reach approximately towards the minimum. The answer don't need to be accurate, but this would give me a good enough abstraction of the problem that I'm trying to solve. That is a very high level problem which can't be solved by rules. So this is the main idea when it comes to neural networks, or how does machine learning work. Now what is neural networks in context of machine learning or AI? So AI was the basic abstract idea of making intelligent machine. We talked about rule-based systems in that. Now came machine learning. Machine learning was the main idea, the core idea of machine learning was to learn through back propagation. We don't have to set the initial middle layer by ourselves. That would be automatically done by giving the input and output. Now came a even further abstraction of this concept where we used multiple neurons, right? Multiple neurons to learn something, to learn a more abstract concept, like image recognition, text recognition, and all of that kind of stuff. So to do all of that, what we introduced were neurons. Neurons were single scalars. One neuron is a scalar with a weight and an activation. Now, there are multiple of such neurons whose, when we take an input, the input passes through all of these neurons. It gets multiplied, right, according to the matrix, and then we receive an output, which is the sum of all of these neurons. And this is how it works. So let me show you a diagram of this. The neural network. So this is what a basic neural network looks like. These are the middle layers. Now, on the basic level, what is in the machine learning level, or for the most basic level of neural networks, there is only a one hidden layer, right? There one hidden layer, and the output can be, there can be any number of output. The output is also a matrix. For this example, there are three inputs in the input matrix. It is a 3 by 1. Okay, and this is how all of this is working. So this is a basic neural network, and as there are multiple layers in this one, this is a deep neural network. Now, what was the special about deep neural network? So okay, so by a single layer we are able to learn linear concepts because there is a multiplication of this directly. So these are very linear, the output of these one. But if we want to introduce more non-linearity and learn more abstract concepts, to introduce more mathematical power with our network so that it can learn more, we introduce multiple layers, and between each of these layers there is an activation layer that is a non-linear activation. For example, ReLU, 10H, sigmoid, and other stuffs that can be used, and that is all that is happening. So this is a very basic introduction to what is deep learning and how does deep learning work. So how does deep learning work? What is the point that I want to highlight here? Why am I speaking about all of this basic stuff that you might already know, that you might already have learned through academics? This is very basic, right? Anyone who is watching and stuff like that, उसको पहले से ही पता होगा कि how does this work. But what is the point that I want to highlight here? So the biggest point, the most important point that I want to highlight when it comes to neural network is the fact that when it is done, when the neural network learns, what happen is this is the input. It passes through first layer, then it passes through an activation, then it passes through the second layer, then it passes through an activation, then it passes through the third layer, and then it passes through a final activation which gives us the output. Now we calculate the loss on this output, and the loss is back propagated layer by layer. So the loss, only the final layer, so the loss is propagated layer by layer like this. When we calculate the loss here, the loss first passes through the gradients through the third layer, then it passes through the gradients of the second layer, then it passes through the gradients and changes the weights of the first layer. Now what you can instantly realize is that only the third layer, only the last most layer of this neural network is capable of learning anything about the loss. All of these layers just learn from the second layer, from this layer, and what it knows about the loss functions, what its gradients are about the loss function. When it comes to the first layer only is capable of learning about the neural network from the second layer and the third layer. So the first layer changes its representation according to what the second layer demands to reduce the loss function, and the third layer reduces its loss functions according to the loss, but the second layer reduces its loss functions as per the demands of the third layer. So when the representation is happening, first layer doesn't know much about the final loss, second layer doesn't know much about the final loss, only the third layer knows about the loss, and the second and first layers changes their weights according to the corresponding demands of their future layers, of the layers that are going to come after that. So okay, this is how a basic neural network learns, and this is what is called representation learning, because the initial layers are trying to represent the input that is given to them in such a way that allows us to extract essential features from our input data and create the output that is necessary for our task, for example image classification and stuff like that. So okay, this is a very basic introduction to what is deep learning and how it is working. And now we are going to start with our implementation. So let's open up Google Colab. Why not? Why to put load on your own machine when you have such amazing cloud computing networks available? Hmm. So I guess this part is done now. There's some way to make a check. I know this is not necessary, but a second. There must be a tick symbol, right? Fuck. Why is this so stupid? Why is Google Word so stupid? Come on, guys. Make Google Word not stupid. Okay. So there must be a check tick. Tick. Yep. There we go. This part is done. Now we are gonna implement a basic deep learning network on the CIFAR 100 dataset. So how it goes. So what is CIFAR 100 dataset first of all? Let's look at this. So this is a basic CIFAR 100 dataset. So in the CIFAR 100 dataset, there are 100 classes of images, right? There are 100 classes of images that needs to be classified. There is a 32 by 32 by 3 images of different classes, and the our goal is to output the class of an image based on its input value. Right, based on the image we need to classify what kind of image it is. So it is an image classification task basically, and if any of you is aware of the terminology used in neural networks, so this is the basic task we are going to perform. So let's see, we are going to use PyTorch, and for everyone who currently uses TensorFlow, I'll definitely suggest PyTorch if you want to dwell into the research side of deep learning, because PyTorch implementation allows a lot of abstraction and is completely low level as compared to TensorFlow. TensorFlow works on a very high level, okay? So it makes it really difficult to change the training loop and stuff like that, because you have to change the source code for it, and you have to override the methods that are initially defined in TensorFlow, which gets a bit annoying, and you can't do stuff with that. There are a lot of restrictions because some functions are designed to work in that way, and it is great. It is one of the most commonly used deep learning framework, but one of the biggest advantage that it introduces is during the form of implementation. When you are trying to make a uh, production ready deep learning model, then TensorFlow can work great. It is very easy to do that with, and it automatically detects your GPU. You don't have to do much, you just have to install the necessary drivers, and it will automatically do the fastest training for you. TensorFlow is a bit faster than PyTorch, but when it comes to PyTorch, the one of the main networks, one of the main things that you use when it comes to PyTorch is its optimizers and its basic uh, autograd function. Autograd function is a function that automatically calculates the gradients of something with respect to a particular function of all the various things we have discussed before that. So all the different operations we do to reach a particular output. Now, if I define a autograd based on that output, it will calculate the gradient for each of the layers, each of the things in between automatically based on that output. So take the partial derivative of that automatically. That is one of the main features we used about PyTorch. Then we also use layers, and we also use datasets. So okay, so let's get started. So first of all, let's key steps. Let's define the key steps here too. So what we are going to do is, first of all, we are gonna oh, import the dataset. Now the dataset is already pre-processed when it comes to PyTorch, so we don't have to do much in that. That would be automatically done for us. There is no much of data pre-processing here. So then we'll define our neural network. Test our neural network. Uh, we'll train it. Calculate validation and training process. Ensure them for no, what do we call it? Documentation. And after that, we're also gonna do improve our neural network. That's all. That's all. That's the basic things we are gonna do. So let's get started. Let's first import our data sets. So let's import Torch first of all. And let me change the runtime for GPU already, as it will get really annoying really quickly. And let's connect. So okay, now let's import the data sets. How are we going to import the data set? The data set is already there from Torch vision dot data sets port, and it must help us here. Well, used to automatically tell us, right? Yep. Hmm. Yep, these are basic import statements. No module name, torch vision the details. Yeah, think it's torch vision. I don't think that's what it's called. Okay, now let's start by importing our dataset. So I don't think we need this. We'll need this. Okay, so get data. PyTorch. Yeah. It is a learning process. Okay, I'm also learning to write things better. But now I have to follow a lot of documentation. First vision datasets 400 plus 400 root train transform. You don't need to transform this, right? You'll see. If we need to transform it, will transform this dataset. But I don't think that would be necessary. I think that is already normalized for us, but we'll see. Okay, this is the basic format. Okay, that's annoying. The hell? Yeah. Now we don't need this. We don't need this. And none of this. We need so that's a train data. Train is equal to 2, download is equal to 2. Test data 100. Root is equal to test. Train is equal to false from a download. So this is just the basic way of importing dataset from PyTorch. There is not much to do in it. Anyone here? We have one person. Who is that? I don't think there is anyone here. Does anyone matter anymore? I don't know. Let's see. This is how we are going to import our data. It is downloading. Okay, data is downloaded. Let's see. Data dot ship. Is that possible? Yeah, it's far under object. Yep. So what we have to do is now we have the train and the test data. Now, as much as I can remember, you have to load this to a data set. Wait, train data this x is equal to blah blah blah. Where is it? Nah, you don't need to do it like that. Yep, this is the stuff we need to do. So train loader is equal to data loader in data batch size. Let's keep it okay. Let's follow good coding principles. Let's introduce batch sizes and hyperparameter, and let's keep it to 8 for now. 8 is a good batch size, decent batch size. Train data, and let's shuffle is equal to true, so that we don't get the same class of images over and over again. That's it. So now if I do next train loader, should give me um hmm, data. Okay, sorry. Next. Next. So we need to make it iterable, and then this. Okay, that's weird. That's just weird. That has never happened before. Let's follow this then. Oh, what is it saying? I don't need random horizontal flip. Just need two tensor, I guess. The transforms. Where is transforms? Torch is under transforms. Before this, let's introduce transforms. I don't want this. Transform set compose. Install. Now when we compose dot init takes two positional arguments, but three were given. Then how do we do it? Okay, we have to make a list of this. Okay, let's make a list of this. Okay, now it should work. And now what we do is ये चीज हो गई. अब अपने पास ये आ गया. अब इसको अगर हम ट्रेन लोडर को जब हम लोग कॉल कर रहे हैं, ओके आई शुड हैव डिफाइंड दैट बिफोर. ट्रेन लोडर को जब कॉल करते हैं तो यहाँ पे हमें लिखना पड़ेगा ट्रांसफॉर्म transform transform. So train loader is one that gets that. Or no? No, train loader doesn't get that. Train loader gets that. No. Okay. I get it. I remember that. तो टेस्ट ट्रांसफॉर्म के अंदर अपने को ये करना है या फिर सिर्फ ट्रांसफॉर्म, और फिर यहाँ पे जो हम इसे कॉल कर रहे हैं ट्रांसफॉर्म और यहाँ पे अच्छा इसको कॉल नहीं करा मैंने. डाटा ट्रांसफॉर्म, दिस इज व्हाट वी नीड टू कॉल. Yep, this is it. Now this is working. Now this should work. Now this should work. And now this is working. Let's see data.shape. Or data. Let's print this out. So yep, this is it. This is working perfectly. So what we have here is, let me explain whatever we have done till now. This is the data loading part completed. So let's make a whole cell for this data loading. We'll try to keep our code as organized as possible so that it is better to do experiments with it. And above that, let's find HyperParameters. So this is the only hyperparameter we have encountered till now. And when it comes to data loading, so first of all we introduced a transform. In the transform, what we did is we first normalized our layers, because it is important that we normalize. And this should be data transform. It will give us errors in the future, so why not fix this? And so first of all, we have introduced a transforms layer. What this layer is doing is basically we are first converting this input that are getting from CIFAR 100 to a tensor, because we'll be working with tensors when it comes to PyTorch, and then we are normalizing it to 0.5, 0.5, 0.5, the mean being 0.5 and the standard deviation also being 0.5. So basically the most of our output, the one standard deviation of our output would, which contains around 90% of our data, right? So that would be contained between 0 and 1. So that's what we are doing. Now we are also calling the train data from CIFAR 100 in this directory. The root being dot means it will be called in the current directory that we are working it. Here you can see the CIFAR 100 PyTorch target. This is already introduced there, and then they also expanded this into test train. So this is what we have basically done. Now we made two data sets: train data, test data, and we have set the download to true. This is a basic operation to call the data from the PyTorch server to our server. After that, we have made a train loader. Now when it comes to PyTorch, you need to work with data loaders. What data loader does is, whenever we call a next iteration of a data loader, the next iteration of a data loader, it will basically, why is this missing? This is not needed. And what I was saying was the basic work. तो डाटा लोडर का बेसिक काम क्या है? डाटा लोडर का बेसिक काम यही है कि जब भी हमारे पास डाटा सेट आ रहा है, उस डाटा सेट के अंदर हमें मैनुअली ऐसा कोड लिखना पड़ता है कि उसमें से शफल डाटा सेट आ जाए, या फिर वैसे उसके लिए और भी लाइब्रेरीज अवेलेबल हैं टेंसरफ्लो में, बट पायटॉर्च की जो लाइब्रेरी है उसके अकॉर्डिंग एक डाटा लोडर फंक्शन होता है. डाटा लोडर फंक्शन को हम लोग डाटा सेट देते हैं, उसको बैच साइज बताते हैं और उससे बोलते हैं उसे शफल करना है या नहीं करना, क्योंकि जब टेस्टिंग होती है तो कई बार शफल ना करना बेटर होता है, क्योंकि सेम इनपुट बार बार दिखते हैं और हम वेरीफाई कर सकते हैं चीज़ें कैसे वर्क कर रही हैं, बट दैट विल बी नॉट बी नेसेसरी इन आवर केस. और बेसिकली ट्रेन लोडर ये काम कर रहा है कि उसने ट्रेन लोडर सेट कर दिया. अब वही मैं इंस्टेंस करके दिखा रहा हूँ कि अगर मैं डाटा को कॉल करूंगा, डाटा को नेक्स्ट इटर से, पहले इसको इटरेटेबल बनाना पड़ता है इटर फंक्शन से, और फिर उसका नेक्स्ट वो कॉल करना पड़ता है. तो अगर मैं इसको कॉल करता हूँ, दिस इज जस्ट द टेस्टिंग इंपोर्टेड डाटा. तो हमने उसे टेस्ट करा. टेस्ट में हम क्या कर रहे हैं, हमारे पास जो डाटा आ रहा है वो इस शेप में आ रहा है कि हमारे डाटा सेट के अंदर एक लिस्ट है जिसमें दो ऑब्जेक्ट्स हैं, जिसमें 0 वाला हमारी इमेज है और जो 1 वाला है वो उस इमेज की क्लासिफिकेशन है कि वो इमेज किस क्लास को बिलोंग करती है. तो एक बार इसको दोबारा लिख के देखते हैं. सो यू कैन सी जो पहले वाली है उसको 8,3,32,32. Now again, why is this 3,32,32 not 32,32,3? Because TensorFlow में channels को लास्ट में रखा जाता है, but when it comes to PyTorch, channel वाला जो हमारा लेयर होती है उसको हम as first dimension रखते हैं. First dimension is 0, 1, 2, 3. So first dimension में हम लोग channels को यूज करते हैं when compared to TensorFlow, जिसमें लास्ट वाली जो डायमेंशन होती है उसको चैनल्स के लिए यूज करा जाता है. और ये 8 का इसीलिए है क्योंकि इट इज जस्ट अ स्केलर दैट रिप्रेजेंट्स व्हाट क्लास इट बिलोंग्स टू. सो ओके, टू टेस्ट दिस आउट, लेट्स आल्सो राइट अ कोड. let's write a code. Let's not do it like this. So basic way of doing this is, more cleaner way of doing it would be images comma labels. So this is what we are abstracting from this, and for image comma label in zip images comma labels. Now see, basic Python is really essential when you're working with these things. So this is what we get, and now what I will do is, let's import matplotlib just here. matplotlib.pyplot splt, and here what we'll do is plot imshow and our image we are getting. So let's see, what I was saying was image.shape. So what should happen is, what we should get from here is image. Oh, okay. Let's just define it like that. That's more cleaner. So if should have printed this. But there, it reset. Why the fuck did it reset? Session crashed for unknown reasons. I hate Google Colab. I hate Google Colab. I honestly hate Google Colab. The fuck was that? Stupid, stupid, stupid. Get plot.im show image.permute. Now, what is this permute function? Let me tell you. So, as I said, basically, whenever we represent images outside of PyTorch, we represent them in the form that image dimension, width, height, comma channels. But when it comes to PyTorch, it represents the image like channels, width, height. So to deal with this, what we have to do is when we are passing it to matplotlib, we have to permute, and where we tell the first dimension is becomes the zero dimension, the second dimension becomes the first dimension, and the zero dimension becomes the third dimension. So we are basically setting the channels to the last layers. And so this is plot.im show this, and I would also like to do comma. There must be a way to X label, right? Label this. Interpolation, none, aspect, none, alpha, V minimum, V maximum, nah, doesn't matter. Return home resample. Dot I am sure documentation. Let's see how matplotlib works. Let's learn. We are learning right now. Can't argue with learning. ये सब ठीक है, मैप ठीक है. Pick text. No. Give text label with let's do it like this now. Pick this is equal to plot.subplots, and the size we are looking for is, let's give it 4,2. Why not? So what the hell is happening? I love PyCharm. I hate Google Colab. It is not the perfect development environment, but we have to code here because of the GPU, because we don't have a GPU. That's sad. That sounds sad. Let's even enumerate this. When we enumerate, we'll get an I, comma, all of this. And we'll set axis. Okay, this is so annoying. Let's just do it like this for now. Let's see how this goes. And for now, let's basically print label. Okay, and we are doing this for one image for now, as we are exiting the loop. Oh my god, why does this keep resetting me? Why does the runtime get reset? The fuck is this? Does anyone know what this is? So stupid. So stupid. Fine. Let's do this. Okay. Doesn't even matter. I'm not even using it. Numerator. Okay, this is so stupid. This is so stupid. Let's remove this. What is the problem now? Oh, the fuck is this? Fine. Why the fuck does my session keeps on crashing? Does anyone know what this is? Why are there so many labels getting input? This doesn't look right. Let's not normalize for now. Just to see where the data is initially. Just to see where the data is. Bro, session keeps on resetting. Okay, now let's also print this to see where it is normalized to. I don't even know what that is. What the fuck is this? Is this some sort of hat? Print image, right? Let's see what the range is here. Oh my god, did my session? Bro, I'm not working with this stupidity. File, save, download, type in, desktop, save. This is so annoying. So much annoying. I don't know what the hell is its problem. Let's change our account. Maybe that will help. I don't know, but that was so annoying. That was so much annoying. Bro. It is so annoying. Is this working now? No, I don't. I don't want it. Oh, fuck. You keep crashing me. I don't care. Okay, fine. Here we go. Once again. I'll have to download this. This is so annoying. Can I just say that? Google Colab is annoying. I don't think it is worth it to pay for Google Colab because the session basic CIFAR classifier, right? I'm not a robot, thank you. What's the runtime? Okay, so good. At least something it can do right. Let's just import this. What the fuck? Okay. Let's be calm here, guys. No need to worry about. Let's just all be calm. Invalid syntax. Data loading. But I just okay, I pressed something. Make fair to you, Google. Fair to you. That was my mistake. That's my bad, guys. I'm not a person that hates everything. I'm not a person that is blaming things on Google. It was just not working. Okay. Now it is working, so I'm not blaming it anymore. By the way, I like this art theme, so it is overall a good decision to switch here. I think I'll be able to work here better. So this is basically the data we have. Let's see. So we learned data loading by now, and we are currently working on data loading right now. Again, so this is it. Now tensor 12. Now, okay, see, I told you it must be already normalized. I've worked with these data sets before. It is already normalized between 0 to 1, so I don't need to worry about that. See, that's good, right? And I think I have to give an exit code to really exit the loop. That's why it is not working. Oh my god, my session keeps crashing. My session just keeps on crashing. Fine, fine, fine. We'll work with this. Oh, no problem. No problem, Google. You can't irritate me. The exit code is not working. It shouldn't print all of this. This should work. Okay, I can't work with this. Um, do I have it? Do I have PyTorch? Let me just test. That must be for me. Um, let's see. Python. Python. Yeah, I guess we'll have to work with this thing. Maybe, yeah, we can work with Python, right? I know here, right? Which one? This one. I have working PyTorch here. So let's see. So instead of all of this bullshit, what we'll do is we'll make a new folder here. And that's too much work. Wait, we'll work with this for now. We'll see how it goes. So this is breaking now, right? So this is this, yeah. So here we go. This whole neural network, this big, but why am I saying neural network? So this tensor right here, this tensor represents a image. This tensor between 0 to 1. And this is the class of image. This image is a class of 38. Now let's see what is 38. Now let's CIFAR 100 classes. I'll find it. I don't know. This is so annoying. Let's run this again. I hope my session hasn't crashed abruptly. What the fuck is this? Oh my god, that's a scary image. I don't know what that is. Even I don't know what that is. So stupid. How can a machine predict when I can't? Okay, this is a tree. So I guess 72 must be tree. 500 class 72. 500 class 72. Is there no data about this? What number represents what class? That's so stupid. Let's do it this way then. Okay, I don't care. Fine. This is what it is. This is what we're working with. We can use CIFAR 10. We can use CIFAR 10 to make it more easier. Yeah, let's use CIFAR 10. Why not? Like, this is not working. But we'll make this too basic. That would make the example too basic. We have to use a network that has more things to learn. Should I use CIFAR 10? Let's use CIFAR 10. It's not working out for us. Yeah, fine. I'll change it. Yeah, download this. Download this. This is stupid. You're not working with that. That's stupidity. Even I can't classify those images. What do you think I make of this? What's this? Nothing. That's what it is. I need, at least, we should have a better data set. I don't know. Is that any better? Okay, this is some kind of animal. This might be a deer. You see, this is even more explainable, right? This is at least it makes sense. It is visible what it is. We can deduce what it can be. So that is good. We'll accept it. My mouse has died. And now, after all of that, so we have been able to print this image now. Now we know how our data set is arranged. So we have these tensors. These tensors represent our images, right? So here a tensor. This is the final tensor must be between 0 to 10. If I print all of that, you can see that. And this is what our data set looks like. So when I do this, I'll get an image that images that are of the size 8, 3, 32, 32. Now 8 is the batch size there, 3 is the number of channels, 32, 32, are the height and width. The label is a 1 by 1 tensor that would be between 0 to 10, and that label represents what our input is. Now one more thing that I would like to change here. One more thing, I like to one hot encode these labels. Okay, before doing anything. So let's see. One hot encoding in PyTorch. I've done that before, but let's see. It's better to look at such things. Nah, that's too complicated. It's, you know what would be better? Instead of using the labels directly like this, what I'll do is, now I'll not print label. I'll make a OneHotEncoder of myself. So we'll write a code. Def OneHotEncoder, and it will take in a label. And what it will do is, when it takes in a label, it will have a matrix array torch.tensor. Let's have a simple array, right? Use a simple array work. This should work, right? Have I not run that cell? Yep, this is working. So the second class must be a car. Let's run this a few times to get the hang of this. It is working correctly for all of the data. Let's, you know what? Let's just do this and then run this. Let's see. Okay, plot.show. That would work. Now it will show it every time. For each of the image, it will show it individually. That's what the use of plot.show is, guys. Otherwise, the Google Colab would instruct it to plot.show after all of the images have been made, and the final image that would be made would be the last image. So if you want to show every image, you will have to insert a plot.show in it. So there's the tensor. This is our class. So the first class must be an aeroplane. Second class was a car, as we saw. Third class is some kind of a bird, I guess. And again, third class is the bird. Correct. We are correct. This is a ship. Second class is a car, so we are definitely correct about that too. And yeah, so OneHotEncoder is working. Now we have a OneHotEncoder. Great. So testing imported dataset has been working. Now let's define our neural network. That's the fun part. So I've already imported everything that is needed. Okay, no. Not port torch.nn as nn, and let's start defining. Okay, so this is the fun part. So now we have finally imported our data set. Now the data set is working. We are using CIFAR 10 instead of CIFAR 100. As CIFAR 100, the images are not even clear to me as such. So what's the point? It doesn't matter. So let's see this. Now, when it comes to PyTorch, when you have to define a neural network in PyTorch, you have to use classes for it. So it is a very Pythonic way of writing, and you make things in module. So PyTorch allows you to write code in a very modular form when compared to us other platforms like TensorFlow. They are not so modular. You have to use Keras functional library for it, and the functional API, yeah, you can learn that. That is also workable. But see this, when you're working with TensorFlow, you have to use two different kind of formats. That is a functional, and one is the sequential, the basic one that you use. Now there are two different things you have to learn to make everything work. But when it comes to PyTorch, it is so low level that you have to learn just one basic thing, and then everything will work. So okay, Google has started to warn us about the GPU usages. So let's just define our class. So our first defined class is going to be our CNN, our convolutional layer. So con block. Now we have to import this def underscore initialize, and in the initialization, and yep, one more thing that I love to do here while we are here is that when we are loading the data, I can also set where I want to send this, right? Nah, it is not that. Okay, we'll do it individually. It's fine. That doesn't matter. That's not so much difficult. So, yep, init self super, and first of all we have con layer, that is nn dot con 2d, and we have the that's in channels, out channels. What else will we need to define? Kernel size, I think we'll keep it 3 for the most part. Padding, nah, no need to define all of this. We can have a quarks, that's better. Channels, common. We can define every layer like we want. Now, other than that, after that we'll also need a self channels, and after that we'll also need a normalizing layer. So we'll use batch normalization. Keep it norm for now. Norm is equal to nn batch norm 2d, and that would be done on the out channels. Now we'll also need a activation layer, so we'll do nn dot. What activation should we use? In the middle we'll use leaky relu, as that seems to work great for image tasks. So there's leaky relu, we'll be using an alpha of 0.2. Now we'll define the forward propagation. So for the forward propagation of this, what we'll need is, first of all, x would be equal to self dot con layer x. Now x is equal to self dot norm x, and x is equal return self dot x. Right, this is what we're gonna do. Now how? So okay, so this is how we have defined a con layer. So ओके दोबारा समझते हैं क्या करा. डाटा सेट रिपोर्ट हो गया, वो सब समझ आ गया, क्लासेस हो गई, वन हॉट एनकोडिंग कर दी. वन हॉट एनकोडिंग हमने खुद की समझ के बना दी, बिकॉज वाई नॉट, वी कैन, है ना, बिना बात पायटॉर्च की डॉक्यूमेंटेशन के थ्रू वेरी करना पड़ता है. दिस इज जस्ट अ 2 लाइन ऑफ कोड. आफ्टर दैट यहाँ पे हमने एक कन्वोल्यूशनल ब्लॉक डिफाइन करा है ना, ये ब्लॉक हम मल्टीपल टाइम्स यूज करेंगे, तो इसलिए मैं इसको एक बार डिफाइन करके रख रहा हूँ जिससे हम इसे बार बार यूज कर पाए। इस ब्लॉक के अंदर सबसे पहले कन्वोल्यूशनल लेयर के थ्रू पास होगा हमारा जो भी इनपुट होगा, फिर वो नॉर्मलाइजेशन लेयर से जाएगा और फिर वो एक्टिवेशन लेयर से जाएगा। एक्टिवेशन में बीच की लेयर्स में लीकी वैल्यू रखने वाला हूँ, और फिर एक फाइनल लेयर होगी जो डेंस लेयर होगी, और वो होगी सिग्मोइड एक्टिवेशन फाइनल आउटपुट के लिए। क्योंकि फाइनल आउटपुट जो होने वाला है वो एक 1/10 का मैट्रिक्स होने वाला है, जिसके अंदर हम लोग या प्रोबेबिलिटी होगी उसके अंदर कि हर एक क्लास के होने की कितनी प्रोबेबिलिटी है। सो दैट इज द मेन ऑब्जेक्टिव वी आर वर्किंग विद राइट नाउ। एंड अगेन right now in this part of the video we are currently on this part, PyTorch implementation of CIFAR 100, then we'll have to improve our data set. So that is all the good stuff. Abhi ke liye this is the very basics of it, I'll say. We are just learning the basics, we're just getting a hang of basics. Now again one more thing to notice here is normalization is used before activation. काफी लोग इसको अलग तरीके से करते हैं, एक्टिवेशन के बाद नॉर्मलाइजेशन यूज करते हैं, बट दैट इज नॉट करेक्ट। हमेशा नॉर्मलाइजेशन एक्टिवेशन से पहले होती है, क्योंकि नॉर्मलाइजेशन का मेन टास्क यही होता है कि एक्टिवेशन का जो हमारा जो एक्टिवेशन फंक्शन है, अगर एक्टिवेशन फंक्शन को देखा जाए तो जब बहुत बड़ी वैल्यूज उसके अंदर इनपुट होती हैं तो उसके कारण उसमें प्रॉब्लम्स कोज हो सकती हैं। तो हम क्या करते हैं, पहले नॉर्मलाइजेशन लेयर से पास करते हैं, जो सारी लेयर्स को नॉर्मलाइज कर दें एक अच्छे सेट ऑफ वैल्यूज में, और फिर उसे उस एक्टिवेशन के थ्रू पास करते हैं, जिससे एक्टिवेशन एक अच्छी रेंज के अंदर लिमिटेड रहेगा। एंड नाउ वी हैव डिफाइंड दिस कॉन ब्लॉक, एंड आफ्टर दैट what we'll need to define is our class of main model or module. That's all we need. Mn dot module. So we'll need a first con block. So the conf block. Now in channels, out channels. So in channels in this con block would be 3, because our input image of the size 3. Now we'll take it to 32. Then we'll take the kernel size to be 3, and we don't need any padding there. Then we'll use a average pool, n dot average pool. Right. But this, yeah, I will do later. यहाँ पे ऐसे define करने की जरूरत नहीं है. So self dot con block is this. Now let's keep the size here. But this, so जब हमारे पास x आ रहा होगा, 32x32 का होगा, हाइट एंड विड्थ की अगर बात करें, और 3 चैनल्स होंगे। फिर इस लेयर से पास होने के बाद उसके अंदर 30x32 चैनल्स होंगे। फिर सेल्फ डॉट कॉन ब्लॉक 32,64 कर्नल साइज इज इक्वल टू 3 अगेन। तो इसके बाद उसके अंदर 28x64 चैनल्स होंगे। बट इन मिडल ऑफ ऑल ऑफ दिस हम उसे एक पूलिंग लेयर से भी पास करेंगे, तो उसके कारण उसमें 15x15 चैनल्स हो जाएंगे। एंड आई थिंक इट विल बी बेटर टू यूज अ पैडिंग ऑफ 1, जिससे हर एक वेट को सेम वैल्यू मिले। अगर हम पैडिंग यूज नहीं करते हैं तो कन्वोल्यूशन लेयर्स के कारण जो एजेस होती हैं उनको कम पार्टिसिपेशन मिलता है, तो पैडिंग 1 यूज करने से वो चीज़ रिमूव होती है। नाउ it will be 16x16 after passing through average pool. Now this would become 8x8 after passing through average pool. And let's use one more cone layer, because why not? Cone block 64,128, kernel size is equal to 3, padding is equal to 1. 4x 128. Now this is the, now after this we'll pass it through a dense layer. So nn dot linear, right? Nn dot linear, and 4 into 4 into 128. What is that? That's 2048. So we'll want it to convert from 2048 to 10. Right. So this is it. We'll also use an activation for the final act. Final act is equal to nn dot sig point. Is that the thing? And dot sigma. This is it. Now we define a forward layer. Self comma x. In the forward layer, we'll first pass it through. So we'll first pass it through self dot x is equal to self dot, or we can do it like this, nn dot average out channels is 32. Right भी देनी पड़ती है ना, and then average pool. Kernel size, comma sprite. We'll just have to give the kernel size then. This, it doesn't need to be this. It needs to be 2 because we need to half this. And after that, self dot con 1 x. X is equal to nn dot average pool to the 2 self dot con 2 x is equal to nn dot average pool to the. So we could have defined this, right? Self dot pool is equal to nn dot average. Why to write? So okay, one more programming principle, important programming principle. Always follow the DRY method. What is dry method? Dry method is don't repeat yourself. If you have to repeat yourself multiple times in your code, then it means that your code is not right. It needs to be better. It needs to be cleaner. So never do that. Self dot pool. So this is not good practice. Self dot pool. And here also self dot pool self dot con 3 x and return self dot final x. So now this is working. Let's define a test for this. Def test model. तो हम कुछ नहीं करेंगे. Array is equal to torch dot random. torch dot random और size define कर देंगे 0. साइज डिफाइन कर देंगे 8, 3, 32, 32 और array is equal to array मॉडल से पास होने के बाद आउटपुट प्रिंट आउटपुट. Now let's test this. Okay, sorry. Model takes. Oh, first we'll have. Sorry. Model is. And then neural network equal to model. Output is equal to model. The hell is happening? This is working. This class isn't working. I think this is a naming issue. Okay, so change class. The hell is that? Oh, what the? What is going on? Stupid. That's how you do this. Oh my god. That was the mistake. Don't do silly mistake, guys. Never do silly mistakes. The hell have I write a page? I will do the. That's why we're having a test, right? That's why tests are important. Okay, let's not write all of this. So, what we need to do is test this and output dot shape. Right. It should be what we expected it to be. But no, you also not use that. What the hell, everything is so dumb today. Mat 1, Mat 2 shapes cannot be defined. Okay, so what's the problem? 4 into 4 into 128 करा था हमने. This is 32 by 32 initially. Then we pass it through this, we pass it through a pool, so it becomes 16 by 16. Pass it through this, we pass it through a pool, it becomes 8 by 8. Pass it through this, we pass it through a pool, it becomes 4 by 4. Let's see the shapes. Print x dot shape, print x dot shape, print x dot shape, print x dot shape. That's the best way to debug it. If there is a shape error, you need to understand all the shapes. Okay, so we had this, then it becomes this, then it becomes this. This is all right. Oh, sorry. Okay, I get it. We have to change the view. Can't do it like this. What we have to do is x is equal to dot x is equal to x dot view dot shift 0 comma minus. Yep, that's it, guys. We have the neural network defined. We have the neural network defined for our custom data set. Yep, that is working. So, so two steps are done. We have imported data set and we have defined our neural network. Now we have to train our neural network. Let's also write this all into a one block. What the hell? Why are you being stupid? Remove this. हेलो दोस्तों, क्या आप जानना चाहते हैं मंगलयान की सच्चाई? क्या मंगलयान सही में मंगल पे पहुंचा था? ऐसे कितने ज़्यादा चैनल है यूट्यूब पे भाई. I don't know why. So, ठीक है. All of that, jokes apart. Now we have a defined neural network that is called image classifier, and we have tested it. It works. We have seen the images. Now, let's define our training loop. So before defining our training loop, we'll have to define an optimizer. Now, as any standard sane deep learning person, we'll be using a uh, Adam optimizer. Don't know why I forgot the name. तो ठीक है, शुरू करते हैं. So optimizer is equal to torch dot optimizers dot add. Alright, Google. 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 Come on, man. Okay. I am put torch. Adam. What are the parameters for Adam? The parameters are image classifier dot parameter. Its parameters. Let's see. LR is equal to, let's keep it 1e minus 5. Now again, another hyperparameter. So let's say LR is equal to LR. Now let's define that here. LR is equal to 1e minus 5. Now we are here. Now let's go here. Here we have set our optimizer. Right, now we have our optimizer. We have our model. Now what can we do? Now we can define trend. We set define trend for epoch in epochs. Right. Images, comma labels. Data. Next. Data label. Train loader. Right. Train loader. Train loader. After that, we have to also define our losses. So let's give a history of loss. Train loss. And now for the criteria of loss, criterion we'll be using Torch. Used to call it. We have to use binary cross entropy loss. Torch.nn not BC loss. Torch.nn. I've already BC loss. Google, help me. Don't want to make a spelling mistake. BC loss. Yep, that's right. Just define that. We have defined a sigmoid activation here, right? So we need BC loss. If we hadn't had sigmoid activation, that we'll have had to use another kind of uh, loss, which is BC loss with logits. But as we have defined it with sigmoid, we don't need to use BC with logits. Now let's also define val evaluator. For this, we'll also have a val loader. Val loader is equal to test dataset larger batch size because we don't want to have a bad kind of. I'll explain. So valuation loader, and this will pass our model. What it will do is it will take out the output is equal to images comma labels equal to next iter val loader, and output is equal to model images. Now it will calculate BC loss. BC loss. Model dot. Now we define this so that the PyTorch knows when we are evaluating the model and when, so that it doesn't calculate weights and stuff like that, right? So nn.bc loss of loss is equal to output comma labels. Is there any use case? Model input comma targets. So model input comma targets. So output comma targets real. So yep, this is right. So loss is equal to this. Let's print loss. Right. Model is defined here. So call it print val loader evaluator model. Right. This should work ideally. Yeah, sorry. This we should define after that. And its name should be model.parameters. Oh, okay. I forgot about our one hot encoder. This is a bit of a problem. So we'll have to do something like our label. Hmm. Let's get well, return करें. This error I hit. Hmm. Okay, this is a sensible error. Where? Yay! Finally. Okay. What happened until now? We have made a val evaluator. So it will calculate the validation loss for us and return the validation loss. And this is working. This is the current loss, 69. So this goes to tell us that yeah, this is not working. So there are 10 classes and we choose any class at random, right? And then the losses will be, yeah, that's obvious. Like, okay, so we have 10 classes, right? So what is the probability that whatever class we select, we're seeing an image, that it would be a right image? So that probability is 1 by 10, right? So there is a 90% error. So 90% is the error rate. So 0.9, right? So it is doing somewhat better than that. Our random initialization is doing okay. So that's great. But that doesn't matter as we're gonna train our model now. Now the model is defined. Now we have one extra function. We have defined our one hot encoder. We have to make a few changes to it to make it work. Now it is working. Right. Now it is working. There must not be any error in this. Yep. And then what we have to do is image comma labels are in this. We've got our images and labels. Now we'll get our output. See, this is the easy step. Output is equal to model. Yep. मॉडल के थ्रू पास करेंगे हम images को to get the outputs. Then we'll pass it through criterion. Loss is equal to criterion output labels. In the val loader also we should make the criterion. And instead of using it like this, use it like this. Right. So this is happening. Criterion labels dot type is equal to output dot dtype. And one more thing we should do is dot to CUDA. Let's define, and this is also a hyperparameter device equal to CUDA if torch dot CUDA dot is available, else CPU. Right. Now with this in check. Now we'll say dot to device. Optimizer is there, criteria is there, model train. Next, images equal to a images. Comma labels is equal to images dot to device. Comma labels dot to device. Right. And this is the loss optimizer. 0 grad loss dot backward, so that we, so first of all we set all the optimizer gradients to 0, all the parameter gradients to 0. Then we pass loss dot backward. Loss dot backward will calculate all the gradients for all the parameters that have gone through the network. Then after the gradients are calculated, we are take optimizer dot step. And then for our purposes, when we are calculating a loss, we'll also calculate it val loss, which is equal to val evaluated model comma criterion. Okay, and we'll add losses. Val loss will equal to mean losses dot append loss Val losses determine val loss. Then we'll take a step. That's it. Let's train our network. That's the loop. That's the training loop. Optimizer.step comes after loss.backward, because once the loss has calculated the gradients, then the optimizer will take the step according to those gradients and change the weights, and this will keep happening. So let's also have a print statement. Print epoch is equal to epoch comma loss main loss is equal to loss comma val loss is equal to val loss. And just to make sorry. यार अब सही है. No, the model should be training. Ah, man. Where is it? OneHotEncoder labels. That's what we have to use. Now this should work. CUDA or CPU? How? How is that possible? Change everything to device. कहाँ पे? Binary cross entropy में output हमें टू डिवाइस करना पड़ेगा. Oh, okay, these ones, right? Let's change it here itself. Now it should work. We don't need to do anything to the output, obviously. That doesn't make any sense. What the fuck? They are on the same device. They are on the same device. Input type is यहाँ पे क्या? This is really important. ये बहुत ज़्यादा common होता है PyTorch में, and it is really important to understand this. कि कौन सी चीज़ें कौन सी device में. When you are doing parallel processing, if you have more than one GPUs, this really helps. this really helps you achieve that. TensorFlow खैर ये सब ऑटोमेटेड कर देता है, so yeah, we can say यहाँ पे TensorFlow के benefits दिख जाते हैं. But that was working. Why is it not working anymore? Have I changed something? That was just working. What the hell do you mean? Only integer tensors of a single element can be converted to an index. Only integer tensors of a single element. कितनी बार रन भी हुआ है वो. The fuck is this input? ये कैसे आ गया? नहीं यहाँ पे कुछ गलत करा गया. Oh my god, that was so dumb. Okay. Now everything should work, and let's not have that print statement, otherwise it got super annoying. It's not easy. तो ये सब हो गया. Now this should work. The loss is getting down. So our model is training correctly. Wow. Did that actually happen? CUDA got out of memory? What the hell? On a 16 GB? But this is too much, I guess. I run out of space, computational space. What the hell? How is CUDA running out of memory in all of this? Yes. Okay, let's not use CUDA then. Let's use CPU. How much time would it take, right? This is a basic network. Let's just use CPU. What do you have for me now? Bro, that can't be possible. I'm not accepting that shit. Okay, yeah, that's it. I get it, why it's happening. That's because some of them are not changed. It is pretty fast, and the loss is going down. We have got this working. Good. The loss is going down. Great. Yep. So that's what we have trained. So we have completed this step now. We have trained our neural network. Let's edit this. Because the loss has gone down. This is done. This is done. Training our neural network is done. Now our neural network is getting trained. Now we are also calculating this and storing them. So this is also working. Improve our neural network. This is the last step. And we'll just do a small improvement. We'll see. We'll see how much accuracy we get with this and what are the benchmarks. And we'll just try to change that model into a new training loop.
गरम जल्दी होती है ना तो बटन ऑफ कर लेना
गेट ढुका दो यार. Why is it taking so much resources? Am I doing something wrong? Maybe I have to. This storing is going there. Okay, let's save this. What we'll do now is, okay, this is done. We have a training set. Let's download this on the desktop. It's fine. We'll clean the desktop afterwards. Let's for Amazon SageMaker. SageMaker Studio. Right. This is the good stuff. Now I think the only problem was that I can think of is that यहाँ पे जब मैं स्टोर कर रहा हूँ ना उसको तो वो क्यूडा के अंदर स्टोर हो रहा था and this was causing all the trouble. So अब उसको explicitly we'll store inside the CPU and जो भी background में चल रहा है उसको हम ऐसे store करेंगे. And rather than that, one more thing that we can do is कि हर एक iteration का store करने की जगह let's store this also like this. So now we'll only store at every 50 iterations. So that should also save us some memory. Right. So this is working. What's the point of even making changes here anymore? Let's use GPU or maybe just CPU. I think the speed was fine. It's not that slow. What's the point of wasting resources? That would be helpful for someone else. So अब हम क्या कर रहे हैं? We have a working model. जैसे यहाँ पे देख ही सकते हैं इसका लॉस रिड्यूस होना स्टार्ट हो गया था. We'll also be able to test it afterwards. Validation loss भी काफ़ी इक्विवेलेंटली रिड्यूस हो रहा है तो ट्रेनिंग से. तो अभी ये मॉडल ओवरफिट भी नहीं कर रहा था, which is great. Now let's just open. I think this is right. So we have a basic working model of a CIFAR classifier. We have used convolutional layers. We have used 3 convolutional layers which are using leaky ReLU activation and intermediate layers, and is using a final sigmoid activation to output probabilities of it being a particular class for 10 classes. Yeah, this is a CIFAR 10 dataset. So let's open this project. Open up. That's good. Now we have our project here. And all we have to do now is let's upload our file, basic classifier. And here I'll make a few changes. I'll make it CUDA again. Always write this line if you are trying to make your phone more portable. If you ever get into a device that don't has CUDA, this would be helpful. That's why I always use this line. Let's run this. Oh my god, there's no PyTorch in this one. Install torch, vision, torch. Now that this is happening, we can try to understand what our new idea is. So हमने अभी तक जो भी डिस्कस करा दैट इज द बेसिक लर्निंग ऑफ अ न्यूरल नेटवर्क. सो बेसिकली कोई भी जो न्यूरल नेटवर्क होता है वो इसी तरीके से लर्न करता है. और इसमें हम एक और चीज़ इंट्रोड्यूस करेंगे आगे जाके जहाँ पे हम टाइम कैलकुलेट करेंगे कि कितना टाइम लगा ओवरऑल ट्रेनिंग के अंदर, बट दैट इज़ द नेक्स्ट स्टेप. सो उसको भी देखते हैं. तो बेसिकली हमने अभी तक क्या डिस्कस करा कि अगर हमारे पास एक न्यूरल नेटवर्क है तो उसको अगर हम ट्रेन करते हैं तो हम उसे लेयर बाय लेयर ट्रेन करते हैं और हर एक लेयर उससे नेक्स्ट लेयर से सीखती है. और बट जो इनिशियल लेयर है उसको ये नहीं पता होता कि फाइनली आउटपुट क्या है, उसके अंदर वो वाली इंफॉर्मेशन नहीं होती. तो ये इंफॉर्मेशन कहीं ना कहीं लैग करती है किसी भी न्यूरल नेटवर्क के अंदर. तो अगर हमें उस चीज़ को इम्प्रूव करना है तो हमें एक ऐसा ट्रेनिंग बनाना चाहिए जो जिसमें हर लेयर को पता हो कि फाइनल आउटपुट लेयर क्या है, इसमें हर लेयर के पास वो वाली इंफॉर्मेशन हो. तो अगर हमें ऐसा न्यूरल नेटवर्क चाहिए जिसमें हर लेयर के पास फाइनल लेयर की एक्टिवेशन हो, तो उस चीज़ के ऊपर जो है मेन चीज़ है जिसके ऊपर अभी हम लोग वर्क करने वाले हैं, जो मेन मॉडल है जो इसके बाद हम लोग इम्प्लीमेंट करेंगे. सो दैट इज द मेन पॉइंट ऑफ दिस वीडियो. और उसके अलावा अभी तक जो की पॉइंट्स हमने हाईलाइट करे वो यही है कि नॉर्मल नॉर्मल न्यूरल नेटवर्क्स don't have any information about the final layer, about the output. Initial layer. A network where each layer can learn the output. हो गया. Now let's run this. Come on bro, there is a model approach. Approach. There is something. ये तो वर्क कर रहा है. Why is it not working here? Hey, what the hell? Must have not been loaded correctly. अरे we can't even use a CPU here anymore. Great, that's just great. That's so stupid. Okay. Yeah, this is so annoying. Okay, now it's normal. Let's test it out here only. Let's see, let's see. Okay, nice going. Thank you. Um, yeah, one more thing. Sorry. Sorry. And, dot. Let's do 5,000. Maybe 4,000. Let's do 3,000. Okay. Okay. Now it is not crashing. Now it's good. This is where the neural network started to overfit a bit. That's fine. It's fine. It jumped around a bit. So, what are our conclusions from this? First of all, let's test it, right? So, let's test it on an image. Images. Papers. There. और फिर मॉडल इमेजेस और फिर उस आउटपुट को this should return the text, right? Okay. Come on. मेरे में वो सारी इमेजेस हैं. वन के अबाउट करना होगा ना. वन के अबाउट नहीं. चला के आ गया ना. अब इसके अंदर मुझे क्या करना होगा. Good. Different labels. Right. Yep, it is working right. So we can see it predicted it right. Let's try one more. One more. Okay, there is a error in this one. Let's try another. Ship. Okay, and again error. Well, is there some kind of problem? Labels are changing, but the output is not changing. It's too from a long time. No, it is. Okay, so there are a lot of errors. It is predicting some of them right. There are still a lot of errors. Hmm. Errors. So we need to improve our model now. Let's think about this. So first of all, we can observe that final layers में started bouncing a lot. 3-1 तक भी चला गया दोबारा, 2-4 तक भी था बीच में, कम हो रहा था बट बीच बीच में it was bouncing higher. Like we can see 0.21 तक भी पहुंचा है. So obviously the learning rates need to be reduced. तो लर्निंग रेट को सबसे पहले कम करते हैं थोड़ा सा और 1e-6 में भी. बैच साइज ठीक है, बैच नॉर्म ठीक है. न्यूरल नेटवर्क के बेसिस पे क्या चेंज कर सकते हैं? We are using average pool layer. We are using 3 neural networks like this. Channels इस तरीके से हैं. We are using a final dense layer. Let's take some ideas. And classify. And classification. Let's see what are the accuracy they are achieving. Let's see. That I know. That I know. ये सब हमने कर लिया है. ये सब कर लिया है. लोडिंग भी कर ली. Prepare pixel data भी हो चुका है. It was automatically done for us. Let's see. अब देखते हैं मॉडल क्या है इन लोगों का. कॉन्वोल्यूशनल 2D. वाह, इनका भी काफी सेम है. Are they using ResNet architecture? No, 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 no. Okay. They are using 2 convolution layers per layer. 3 to 32 first of all. Padding same है. Wow, this is funny enough. This is exactly the same as ours. Mostly same. What are the results? But are they using somewhat else? What is your best model? 23%. That's it. This is the best model. Okay, we can make these changes to our network. Let's go to con block. We have to use 2 con layer. They are not even using an activation. Okay, there is an activation here, right? इसमें ऐसा होता है. Activation यहाँ है. Normalization नहीं use करी है. I don't know. I don't think this is the best way. Our models. There was a least loss of 0.21. This is, that means 79% accuracy we managed to achieve. So this is not right. This is not right. We are not following this. This is not a good model. We are not doing this. Okay. We are not doing this. Why not? Because it is not working for them too. So instead, what we can do? How can we improve our accuracy? Let's see. What is happening? Okay. So the question is, how can we improve our accuracy even further? So do we have? Can we use a ResNet type architecture? That would be too much. That's not needed. Okay, let's keep our model at this only. Let's plot the losses. Let's plot the losses. Train losses. Start number, end number, one steps. आगे के लिए कर देते हैं. Not about right. In losses. चाहिए 3000 divided by 2 and that works. It नहीं work कर रहा है. उल्टा बनाया मैंने. It shouldn't be like this. Yay! Now we have a plot for train losses. Yeah. एक्सरसाइज भी तो डिफाइन कर सकते हैं. Exercise. Image fig legend fig text. नहीं चाहिए. Wow. This is the kind of image we wanted. So this is the main point, right? This is the main point. We see all of that. Let's change it back to normal. Let's change this back to 20 minus 5. That's fine. One more thing I want to try is what if we use dropout layers? So we'll have to try that. Let's reduce this only. Will it do any better to us? So in that search pool, let's use a dropout. And in the dropout ही होगा ना, and dropout probability is equal to ये, तो 0.322 पे करते हैं. Oh, shit. And then we're doing it like that. Let's do it here. Just drop and then drop out 0.2. Here we'll just use self.out. Self.out. We also will use self. Let's see if this is working. We've changed the learning rate. We have changed that. We're not using that much RAM anymore, so we can train it further. Train it for 10,000 iterations. Train it 10 minus 5. And this is the important one. This is the one that matters. Come on. Okay. This will take some time. This will definitely take some time. Let's have it training. Till then, we should discuss more about what do we do next. What is it that we actually wanted to do? What is the research paper all about? So let's open the Word document now. Because this is where the research paper part comes in, and this is what we actually need to matter. This is what actually matters to us. So let's see. So this is what we have to highlight about the initial neural network training, how our initial neural network is trained, and we have the results for it too, that is getting prepared. Now, let us talk about what we need to research. So, the main idea was that we have done this. Done this, and this will also be done after that, I assume. So let's come to this part, explaining what exactly are we innovating. So let's see what we are innovating. So what I'm doing is, the main idea is, so all of the layers that are trained right now are in a very linear fashion. One layer gives input to another layer, that layer gives input to the third layer, and the third layer gives the final output. Now, through a dense layer, right? Gives the final output through a dense layer. Now, instead of this, what if I train a neural network where I just first train the initial layer, right? I first train the initial layer, send it through a dense layer, another dense layer that can convert the initial layers to the output desired layer, and do this. And I train this. Now I freeze the weights of this layer. Now I freeze the weights of this, and then I make this layer as a locked mathematical computation. Now this formula has been already derived. This know how the output works, and this is the final formula we have. Now the second time I go through the network, what I'm gonna do is I'll take the input, pass it through this locked layer. This will give me an input. Now I'll discard the dense layer that I introduced. Now I'll use this. Pass this through the second layer. Now second layer will have its own dense layer that will pass the and make the output, pass the dense layer that has the input dimensions of this convolutional layer and has the final output of the desired output size we need, which is 10 by 1 in our case. Now if I do this, now I train this layer. Now only this layer gets trained with the help of final layer, and after that I freeze this layer. Now again I get the input, I freeze this layer, I freeze this layer. Now this goes through this first mathematical formula that has been formulated, passes this through the second mathematical formula that has been formulated and frozen. Because of that, dense layers are discarded, they are not needed anymore. And after that I have the third layer, I pass it through that, and there is my final dense layer that converts the third layer's inputs, third layer's outputs to the final desired output, and I use this network and I train the third layer for the final outputs. Now, why is this so important? Why is this dumb sounding idea so important? So let's discuss it once again, and while discussing that, we'll also talk about its importance. Why is it so important? Okay, so let's try to understand this. Okay, तो हमारे पास क्या है, हमारे पास एक न्यूरल नेटवर्क है जिसके अंदर 3 लेयर्स हैं. अभी तक हम उसको कैसे ट्रेन कर रहे थे कि जो थर्ड लेयर है उसको फाइनल आउटपुट दिखता है, सेकंड लेयर को थर्ड लेयर से आने वाले ग्रेडियंट्स दिखते हैं और लॉस दिखता है जो कि एक्टिवेशन लेयर से पास होके आता है, तो उसके अंदर वेनिशिंग ग्रेडियंट वगैरह ऐसी प्रॉब्लम्स इंट्रोड्यूस होती हैं। फिर जब सेकंड लेयर को हम ट्रेन कर, फिर सेकंड लेयर से फर्स्ट लेयर को जाता है, फर्स्ट लेयर को सेकंड लेयर का ग्रेडियंट दिखता है जो थर्ड लेयर से ग्रेडियंट से आया है, जो कि लॉस से आया है, और इसके चक्कर में फर्स्ट लेयर को लॉस का एक बहुत वैनिश्ड पॉइंट दिखता है कंपेयर टू द थर्ड लेयर को लॉस एकदम एक्जैक्टली दिख रहा है। सो इसके थ्रू हम क्या करना चाह रहे हैं, देयर इज अ कॉन्सेप्ट इन न्यूरो साइंस नोन एज न्यूरोप्लास्टिसिटी। सो न्यूरोप्लास्टिसिटी, व्हाट इज न्यूरोप्लास्टिसिटी? न्यूरोप्लास्टिसिटी में क्या होता है, what we say when we talk about neuroplasticity is कि हमारा जब ब्रेन को स्किल को सीखता है, फॉर एग्जाम्पल वी आर ट्राइंग टू लर्न स्विमिंग, राइट? अगर मैं स्विमिंग में एक बेसिक कॉन्सेप्ट ऑफ स्विमिंग सीखता हूँ, बहुत एक बेसिक स्ट्रोक ऑफ स्विमिंग सीखता हूँ, तो मेरे न्यूरॉन्स के अंदर वो चीज़ स्टोर हो जाती है। अगर मैं यहाँ पे वही लूज एब्स्ट्रैक्शन लूँ जो न्यूरॉन्स को इसके थ्रू कनेक्ट करा जाता है विद द एब्स्ट्रैक्शन ऑफ लेयर्स, तो अगर मैं उसके थ्रू न्यूरॉन्स को ब्रेन से कनेक्ट करूं तो काइंड ऑफ न्यूरॉन्स उस ब्रेन की तरह वर्क करते हैं। और एक बार इसको दोबारा एक्सप्लेन करते हैं। तो ओके, तो अगेन हमने ये सारी बातें कर ली कि नॉर्मल न्यूरल नेटवर्क में कैसे सब कुछ वर्क करता है, बट अब अगेन न्यूरोप्लास्टिसिटी का कॉन्सेप्ट आता है कि जो हमारे ब्रेन के न्यूरॉन्स हैं, जैसे अगर मैं स्विमिंग सीखता हूँ, एक सिंपल स्ट्रोक सीखता हूँ स्विमिंग के अंदर, तो मेरे न्यूरॉन्स उस वे में एक्टिवेट होते हैं। अगर मैं उसको लूजली कनेक्ट करता हूँ न्यूरल नेटवर्क से ब्रेन को एब्स्ट्रैक्शन, तो काइंड ऑफ मेरे जो न्यूरॉन्स है ब्रेन के अंदर वो वेट्स अपने इस वे में एडजस्ट करते हैं कि मैं वो वाली स्विमिंग सीख पाऊँ और वो उसके अंदर स्टोर हो जाती है। अब अगर मैं स्विमिंग में कोई और कॉम्प्लेक्स चीज़ सीखता हूँ तो वो जो पहले वाले न्यूरॉन्स थे वो इफेक्ट नहीं होते। वंस आवर न्यूरॉन्स हैव स्टोर्ड समथिंग दैट इज प्लास्टिक दैट डजंट चेंज, तो अगर कोई और इंफॉर्मेशन आती है, अगर हम कुछ नया सीखते हैं, तो एक्स्ट्रा न्यूरॉन्स ऐड होते हैं जो उस इंफॉर्मेशन के साथ जाते हैं, उस इंफॉर्मेशन को एक तरीके से कॉम्प्लीमेंट करते हैं। सो न्यू न्यूरॉन्स कॉम्प्लीमेंट द स्किल्स learned by previous neurons, and as we are on our path to master a skill, more and more neurons keep on adding that complement the things learned by our previous neurons and learned by our previous neurons and provide a more valuable insight. So this is the concept of neuroplasticity in a loose sense, right? When we are comparing. So how am I going to use this concept in neural? So as I told you before, मैं कह रहा हूँ न्यूरल नेटवर्क्स को ऐसे ट्रेन नहीं करते हैं जैसे हम लीनियरली करते हैं, रेदर डीप एक सिंपल डेंस लेयर्स रखते हैं बीच में, जो पहले वाली कॉन्वोल्यूशनल लेयर जब फीचर्स एक्सट्रैक्ट करेगी वो फाइनल आउटपुट के लिए फीचर एक्सट्रैक्ट करेगी रेदर देन सेकंड लेयर के लिए, और वो वहां से जब वो फ्रीज हो जाएगा तो सेकंड लेयर ऑलरेडी रेस्ट्रिक्टेड है फर्स्ट लेयर से, कि जो फर्स्ट लेयर ने सीखा है उसे उसी के ऊपर बिल्ड अपॉन करना पड़ेगा और फिर वो वहां से सीखेगी। फिर थर्ड लेयर रिस्ट्रिक्टेड है सेकंड लेयर फर्स्ट लेयर की लर्निंग से, और थर्ड लेयर डायरेक्ट लॉस में कन्वर्ट करना सीखेगी और उस तरीके से फीचर्स को एक्सपेक्ट करना सीखेगी। So first of all, first thing that is happening by this is our neural network is getting much more interpretable, क्योंकि when we are calculating the loss function, we'll know exactly how much loss has been reduced by each layer। तो अगर हम उसको ओवरफिट करने लगते हैं डाटा को या फिर ऐसा कुछ होता है तो हमें लेयर बाय लेयर पूरा ग्राफ दिखेगा और हम देख सकते हैं एग्जैक्टली विच पॉइंट पे हमने ओवरफिट करना स्टार्ट कर दिया, तो विच लेयर इज नॉट गुड। सो ऑब्वियसली दिस मेथड इम्प्रूव्स let's talk about advantages. So obviously, this method improves. The first advantage being more interpretable neural networks, more interpretable neural networks, making it easier to learn to construct new models by understanding the layer wise loss. First advantage. Second advantage क्या है इसकी? The competition would be much faster. Why would the competition be faster? The competition would be faster because अभी के लिए जब मुझे मैट्रिक मल्टीप्लिकेशन करना और बैक प्रोपोगेशन करना होता है, that is the biggest step. Forward propagation is easy. You can just matrix multiply. But when you have to back propagate, you have to pass it through different gradients. Now, calculating the gradients is a very long step. It is a difficult step compared to the steps we are talking about. So, उसमें काफी टाइम लगता है. तो अगर हम एक सेकेंड, तो अगर हम लोग को छोटा करना है, किसको छोटा करना है, इसको छोटा करते हैं, इसको ये सही. तो अब अगर मैं मोर इंटरप्रेटेबल न्यूरल नेटवर्क्स बना रहा हूँ, पहला एडवांटेज. दूसरा एडवांटेज, मेरा ट्रेनिंग टाइम बहुत रिड्यूस हो जाएगा कंपेरेटिवली, बिकॉज पहले जो मुझे बैक प्रोपोगेट करना पड़ता था, मुझे तीनों लेयर्स के लिए एक साथ करना पड़ता था. अब अगर मैं 1000 ट्रेनिंग स्टेप्स करूंगा तो उसमें से 330 सिर्फ एक को जाएंगे, 330 एक को जाएंगे, 330 एक को जाएंगे. सेकेंड पॉइंट, तो फास्टर कंप्यूटेशन, more generalization and less chance to over. So what is this third advantage? The third advantage ये है कि जब मैं न्यूरल नेटवर्क्स को लेयर बाय लेयर ट्रेन कर रहा हूँ और हर एक लेयर रेस्ट्रिक्ट हो रही है अपनी प्रीवियस लेयर की लर्निंग से, तो कहीं ना कहीं न्यूरल नेटवर्क ओवरफिट नहीं कर पाएगा, क्योंकि सारी लेयर्स एक दूसरे के साथ कॉम्प्रिहेंसिवली वर्क नहीं कर रही हैं. वो एक बहुत बड़ा मैथमेटिकल फंक्शन नहीं बना रही है. पहली लेयर एक मैथमेटिकल फंक्शन बनाती है, दूसरी लेयर दूसरा मैथमेटिकल फंक्शन बनाती है, तीसरी लेयर तीसरा मैथमेटिकल फंक्शन बनाती है. तो तीनों में से किसी के भी ओवरफिट करने के चांसेस कम हो जाएंगे. सो जो ड्रॉप आउट वगैरह लेयर्स हैं जो कि एफिशिएंसी रिड्यूस करती हैं, ड्रॉप आउट रिड्यूसेस एफिशिएंसी. वाई? क्योंकि हम करते क्या है, जब हमने एक न्यूरल नेटवर्क बना दिया, हमने एक बड़ा न्यूरल नेटवर्क बना दिया, अब हम क्या करते हैं, उस न्यूरल के नेटवर्क के अंदर ड्रॉप आउट लेयर्स इंट्रोड्यूस करते हैं जनरलाइजेशन इंप्रूव करने के लिए, विद द आइडिया इन माइंड कि अगर हम लोग ड्रॉप आउट लेयर यूज करेंगे तो उससे रेगुलराइजेशन आएगी. बट एट द सेम टाइम वी आर कंप्यूटिंग अ लार्ज न्यूरल नेटवर्क. हमने इतना बड़ा न्यूरल नेटवर्क बनाया, हमारी स्टोरेज में इतना बड़ा न्यूरल नेटवर्क है, टाइम कॉम्प्लेक्सिटी में इतना बड़ा न्यूरल नेटवर्क है, बट उससे पास करने के बावजूद हम लोग ड्रॉप आउट लेयर्स से पास करते हैं न्यूरल नेटवर्क को. तो काइंड ऑफ वी आर डूइंग वेस्टेड कॉम्पिटिशंस. सो बाय मेकिंग neural networks with this new method where we are training each layer one by one, we are reducing the chances of using a dropout layer, because we don't have to use any of this kind of regularization. Because when we are constructing our model, we can clearly see which layer introduces our uh, 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 overfitting, and we can remove that layer or change that layer into a smaller layer. So this mathematical function formulation becomes much more efficient, and this makes the overall neural network much more interpretable. So this is the main idea we are presenting in this paper. Now I am not sure, with my test the accuracy stays constant. The accuracy of training like that, the previous method that we discussed, that we have implemented here, that is being run right now, the accuracy for this method and the accuracy for our method remains the same from my test cases. And this is the time it took 2 minutes. Let's test this out. Okay, there are still some errors. What is the final accuracy? 0.30. Is that worse? Let's see the training loop. Okay, how do I do this? Will that not work? That worked, but I want to put 10,000. Did I do something? Okay. What the hell? Okay. Right. Yep, but this training looks much more smooth than the previous one. Maybe because of the use of dropout layers. So we have achieved the accuracy of what? 0.7, right? Around 0.7. Uh, yeah, can we improve this further? Can we improve this further? What if we use one more neural layer? More convolutional networks. If we improve this further. Let's see. So for each conv layer, instead of using one, if I use two, let's let's make it a resonate kind of layer. Okay, this is a resonate inspired layer. So what is resolution? This is just this plus x causes the resolution residual connection. Okay, that's it. That's all residual connection is. So that's all we have changed in our network. Let's see how that changes. Is it working? Yep, it is working. Cool. Let's for it to train now. इस तो नहीं चाहिए होगा. It makes sense. Should I? Wait. Stop it. Wait. I have something better. Instead of using it like this on the same cone layer, let's define another one. Let's define another one. So this all remains the same. Define class res block. Oh my god, don't do that. Yeah. इसके अंदर only thing we'll have to change is this will become, I don't need two channels anymore. I'll just need one channel, and I'll be in channel comma in channel. Baki quags self.act, everything remains the same. Self.act x plus x. That's all we're gonna do. So now after everyone we'll have res1 is equal to res block 32 comma 32 comma kernel size is equal to 3 comma padding Um, 4,64, 128, 128. This is it. This is the changes we are gonna make. Now we are using two blocks. Now this should work. Right. But three were given. What the fuck were three given? Oh, yeah. Okay, okay, sorry. This is not necessary. Oh no, what the hell am I doing? 4 channels instead. What does that mean? Everything else remains the same. कहाँ आ रहा है error? 8,64,7,7 to have 32 channels, but got 64 channels instead. There. This should not be happening. Oh. Not really. Yep, this works. This is our new neural network. Let's see. Let's go. Let's train this. Let's see if this training is much any better. We are using res blocks now, residual blocks. Now, we'll also see if we are able to improve the quality from this. Their accuracy was 73%. That doesn't look really great to me. You know, the neural network doesn't look satisfied. So, this is training, right? What is the accuracy we have reached by now? See, we are pushing a bit of the walls. We are pushing the walls a bit. Not that much though. Still stuck. Yep, we are getting better accuracy now. We might have to reduce the learning rate though. Maybe we shouldn't define the learning rate. Adam has an adaptive learning rate, right? Let's see PyTorch documentation. Adam. Oh, okay, no. Yes. we achieved a better accuracy. We got to a minimum of 0.23, so that's great. So we have definitely pushed the walls. That is 77% accuracy. That is higher than that for sure. Let's see the results a bit for ourselves. Yeah, this is correct. This is correct. So see, it has improved a lot. ResNet has helped for sure. Okay, there is one error. Another error. This is correct. So yeah, this is much better than before. And this is the graph. Okay, there is still a lot of jumping towards the downside. Maybe we should decrease the training loss further, or maybe increasing the batch size for the validation loss will help, you know. Come on, this will help. This is a good way to reduce that bouncing around that is happening. Because this shouldn't have happened. That's a too much bounce on average. And learning rate, I guess, let's keep it 5v7 maybe. Let's train this again. It's training. So again, till that, so these are the basic advantages I am looking for. And we'll see accuracy. I'm not sure that time. Quantitative minutes. Experiment that we are conducting right now. We are conducting the experiment right now on the go. Here it is going on. So let's just wait for it. Everything else is working right. So that is the main idea, the core idea. Core idea. Or yeah, that's it. So we have to explain about the previous neural networks. Network, their learning loop. Why it doesn't work? Yes. Training layer by layer where the gradients are back propagated from the final from the loss to the initial layer to the output and hidden layers. Right. Why it doesn't work? What gap space needs to be filled? So initial layer doesn't have much of information about the output. Need a network where each from that. That's the need. That's the point. And other than that, what else do we need? What else was the problem? There are more problems with it. Slow computation because of gradients being back propagated. All layers at once. Another problem is doesn't give much insight about layer by layer learning and losses, making it really difficult to understand what causes what layer is causing overthink or loss reduction and by how much. Need a neural network where each layer can learn from the output directly and the gradients pass for a single layer at once. No need of inefficient methods like dropout. Fast computation time. वो पहले कवर हो गया. More insights on what each layer is doing to both the training and testing loss. So interestingly, while making this idea for the training loop, we are somehow introducing regularization with the help of layers itself, because each layer learns from the final output through a dense layer, and that whole path causes these layers to be fixed after the training. So this is freezed. When we freeze this layer itself act as a regularization because it has learned from the it has learned directly from the loss function, right? When it has directly learned from the loss, it knows what it needs to produce. It knows what the final output should be. So while doing that, we are introducing the regularization with the help of layers themselves. The layers themselves act as regularization because this layer restricts the second layer, because the second layer now has to learn from the abstraction, the representation learned by the first layer. Okay, let's try to understand this in a bit more depth. I'll try to understand this better, okay, because that's the main point. Let's open up Sketch. Diagrams are the best to explain anything. Whatever, dude, whatever. Artboard, let's have a rectangle. I always introduce layers by rectangle. So this is our input layer. Now it's another rectangle. This is our first layer. Now this is our second layer. This is our third layer. And this is our output layer. So how does a normal neural network learn? Is the question. When a neural network, a traditional neural network, let's use good terminologies. So this is how a traditional neural network works. How? So this forward propagates here. This forward propagates here. And this forward propagates here. And this gives us the final output. Now when the loss is calculated on this because we have expected output. And the loss is calculated between these. And this loss is then back propagated to all of these layers one by one. This loss goes to, let's use arrows. This loss then goes to this layer, which sends it to the next layer, which sends it to the next layer. And in this whole process, what happens is this layer learns the representations presented by this layer, which learns from the final output. So this layer learns from the final loss function. This knows how the loss looks like and what to learn from it. Now this layer learns its representations by the demand of the third layer. It learns what the third layer demands. So kind of an overfitting can be seen, right? Because what happens is this becomes a very huge mathematical formula. This whole in itself becomes like a formula where this makes a very big chunk of a formula, because all of these are connected. They are not independent. They are connected. This alters the weight of this alters the weight of this and this. So they are demanding, this final layer is demanding a mathematical formula that is constructed by whole of this. So this causes overfitting. To reduce this, to not cause overfitting, and so that the functions have some independency, there is a layer by layer. One function learns one thing that the second function learns from the first function to output, and then the second function's outputs are sent through a third function that takes the second function's output and learns to output the final layer. So how is that different? So this is this whole, let's group this is our traditional neural network. Okay, my god, so small. Now let's see how our network is different from this. And to illustrate this, we'll copy this, name it new idea. I'll need more space for it, so I'll keep it at the side for now. Very small scale image. So let's see. What we do is, instead of, let's ungroup this first. Can we ungroup this, please? Otherwise, annoying. Ungroup. Thank you. Let's delete this. So the forward propagation still goes like this, but when we are training the network, this is the final propagation, right? This is how it goes. But while training is happening, we define these neural networks, and we have some side dense networks. This was the final dense network initially, right? This was giving us the loss, but instead of this, now we have other dense networks here. इंडी तो पहले भी था ही, इसके भी आगे एक डेंस नेटवर्क होगा ना, मतलब जो इसको इसमें कन्वर्ट कर रहा होगा. So this is how the initial was, but now we have this kind of a structure where we have additional dense network that will discard at the end of training. And how we learn from that? For the first iteration, for the first layer, when we are training the first layer only, we send this to this. Okay, and this network converts that directly to this. Can you see this? This network connects it directly to this. So this is how the first layer is trained. After training the first layer on this, for a few iterations, the first layer has trained its weights. So now we freeze this layer. Let's represent a freeze with a different color. Now we've not finding anything. This layer is now freezed. No, let's use hold. This layer is now freezed. Now after freezing this layer, this lens layer is discarded because now this is of no use. So instead, this layer that has freezed weights, that has learned through the final layer, now gives its input to the second layer. Now the second layer is trained. How is the second layer trained? We train the second layer, we send its input to this network. This is not needed anymore. This dense layer, and this dense layer converts the dimensions given by the second layered output to the expected dimensions. And now this learns its weights. After the second layer has learned its weights, restricted by how the first layer learned its implementation from the loss, and using those representations to finally output the next loss function, these weights are now freezed. This is now freezed again, and this layer is discarded. Now as that layer is discarded, now that second layer sends its input to the third layer, and the third layer already has a dense layer on which it is trained. And now this gets freed. Not even to illustrate, that's how any neural network evolves. The final layer learned its phase and is freezed, And now we have a final neural network, and this is what we'll pass now for evaluations, for training. When we have trained and now we want to use the neural network, this is the whole neural network that has been constructed, and these layers are discarded. Now what I'm arguing is that we are training only one layer at a time. So we have reduced the back propagation weights by 1/3. So the each computation, each time the back propagation is calculated, that is reduced by 1/3. As back propagation is the most time extensive task in this whole process. And now that makes faster computation. Second of all, we have introduced regularization because each layer learns first. Each layer learns through one input itself. So when it is learning, these weights are frozen. So now it doesn't make a huge mathematical function out of this. This function learns to finally calculate the loss function. This function then learns how to use the implementation, the representations formed by the first layer, and use them to give our final output. After learning that its weights are also frozen, and the third layer learns how to use the representations learned by the second layer and improve on the accuracy and output the final layer. So all of this regularizes the network in itself, and we don't need to use any regularization. That's my argument, that this kind of a network should not be making this neural network. This neural network doesn't need regularization and dropout layer, which causes inefficiency. So that's the whole point. I'm not. So that's good. Yes, good. So that was the final explanation. That was the main idea. Now I think the diagram made it much more clear, I hope. I can explain this again. So if anyone doesn't know yet what we are doing, what is the main idea, what are we actually doing out of this? So yep, now it should be more clear. That, and you can ask me again if you want to, if you are just joining the stream. You can ask me, I'll explain it to you again with the help of the diagram that I've just made. How are we training our neural network? What has changed from the traditional neural network, and why I am arguing that this must be better in a multitude of ways when it comes to time complexity, when it comes to the regularization needed for the network, when it comes to the interpretability of the network. Because as you can see, when I'm training it like this, I'll be able to see the training loop layer by layer. So I can see what losses are the first layer able to produce. How are those losses reduced by the second layer? How are those losses reduced by the third layer? Each layer builds upon the initial layer. So if we keep adding more layers, if we talk about extremely deep neural networks that are currently being worked on, when the concepts of large language models have been introduced and stuff, this is the stuff we need. This is what we can help us, right? Because this can help us build upon the previous layer's representations rather than introducing a third layer. So if you want to, if you have trained a neural network before, if you have trained this neural network and you want to train it even deeper, if your data set is getting even more complex, you can just add more layers to this. This is a modular design as compared to the previous models of neural network where you have to train each layer from the beginning if you are trying to introduce a new layer, as you have to do here. यहाँ पे जब हमने अपने न्यूरल नेटवर्क में नई लेयर इंट्रोड्यूस करी, तो हमें कंप्लीटली उसे जीरो से दोबारा ट्रेन करना पड़ा, विच वॉज कम्बरसम, विच वॉज डिफिकल्ट. बट इंस्टेड नाउ अगर हमें डिफरेंट लेयर रेस्ट ब्लॉक इंट्रोड्यूस करना पड़ेगा, देन वी विल नॉट नीड टू डू दैट ओवर एंड ओवर अगेन. That's the main advantage we are getting. Now let's see the loss functions. So this is the best we are able to get, right? This was their loss function and this is the best we are able to achieve. Yeah, this is the very clean training process as compared to the previous training. The validation loss is much smoother. So I guess this is the one we should use, right? Or if anyone else has any other suggestion, that would be great. But yeah, this is what we are using. What was the average loss? How low it went? Yeah, so we were we were around 0.28 for a long time. 0.28. So that's 72% accuracy on validation loss. That's great. That's fine. That works. This was what? 73%. Yeah, that we can achieve. We can achieve that with the help of hyperparameter optimization and stuff, but we are not really going down that road. That's not really necessary. So I think this is the model we can work with. This is our basic classifier. Let's download this. Let's save this. It's important that it's saved. Uh, let's save it here only. Yep. And yep, let's save this. Great. Now we have this. Let's save this too. Basic CIFAR classifier training losses. That's all. Now I'll just come back. Give me a minute. Let's oh let's switch this off for a second. I'm just gonna come back. Yeah, I'm back. Hello. So one more thing that I need to highlight in this paper is that this research is parallel to any research going on in the deep learning community, because this research targets training of deep neural network and should ideally work for any neural network architecture. That's an important point, because this idea of training it layer by layer can be used for any other neural network possible. We are testing it for convolutional neural networks, but that doesn't mean it is not applicable to other neural networks. That's how we are just presenting our test case. And now one more thing I want to talk about is, in this paper, in this experiment, we have not put too much effort into hyperparameter optimization, because our goal is to not generate good results for a specific data set, but instead draw a comparison, right? Comparison between a neural network trained traditionally, trained in our unconventional method. राइट. सो दैट्स वाई, जैसे मैं यहाँ पे देख रहा हूँ अभी, यहाँ पे देख सकते हैं. अब यहाँ पे जो इन लोगों का बनाया हुआ नेटवर्क है, ये बहुत ज़्यादा हाइपर पैरामीटर ऑप्टिमाइज है. यू सी दे आर यूजिंग स्पेशल काइंड ऑफ initialization for their kernels too. So they are using ReLU, they are using max pooling instead of average pooling. They have using SGD optimizers. They are using momentum, a specified momentum. So see, this all goes to signal that they have hyperparameter optimized for this particular value. That's why they are getting an accuracy of 73.5. If we try to hyperparameter optimize this network, we might be able to achieve accuracy much higher than 72% that we are currently at right now. But I'm not focusing on that. I'm not doing that because that is not the goal. हम उससे मतलब ही नहीं है, कोई फायदा नहीं होगा वो करके, because I want to, with the same hyperparameters, with the same everything, what I'm just going to do is change the training loop, and in the expectation that that will improve my neural network training. So yep, that's the idea. And now, as we have done the improvement part, we have come from an accuracy of around 71%, 69% to a final accuracy of 72 point something percentage. That is fine. We, we don't want to push too much efforts into it. So we'll just done this here. So now this part of our video is done. Now we have accomplished one more thing. And we have explained this theorem. So that is also done. Wow, we are making good progress. Now we need to implement our new technique and then write the research paper from scratch. These are the key ideas that have been highlighted till now. Is there anything else to highlight? Hello. Okay. So this is done. Now, what should we do? Should we take a break? Should take a break. Banana and water. That's my diet for today. Hmm. That's the network. Yo, back in the game, Shanky boy. ऐसे वाली, ऐसा करते हैं ब्रेक के लिए, वैसे वाली वीडियोस देखते हैं. हेलो गाइस, तो आज हम पता करने वाले हैं ब्लैक होल के अंदर आखिर क्या है. तो गाइस सीधा चलते हैं ब्लैक होल के अंदर। तब वैसे मैं जो बुक पढ़ रहा था वो दिखाता हूँ, इसमें होगी computational fairy tales. This is a good book, okay? This was a good book. I'll recommend this book. I'll recommend this book to anyone just starting computer science, because this book teaches everything in form of a story. All kind of data structure and algorithms are taught. Good. That's good. You need to learn that. And it has a good story. Yeah. I might be a bit broken. I might be a bit broken. But it has a good story, trust me. I'm not that broken. हाँ, काम करते हैं। हमने क्या क्या कर लिया है? हमने पहली इम्प्लीमेंटेशन कर लिया, उसको इम्प्रूव कर लिया। तो इस पूरे टास्क में से हमारे पहले 4 टास्क खत्म हो चुके हैं, 2 टास्क और बचे हैं, जिसमें कि सबसे लंबा टास्क आई गेस लास्ट टास्क ही होगा। इम्प्लीमेंटेशन तो अब जल्दी हो जाएगी। वी हैव जस्ट टू मेक अ फ्यू चेंजेस टू द ट्रेनिंग लूप, दैट्स इजी, and we can explore some more ideas too if you want to, if anyone. Oh, ऐसा गजब। ये सीक्वल बनाना पड़ेगा, ये सीक्वल हमें ही बनाना पड़ेगा। ये सीक्वल मार्केट में आना चाहिए। द वर्ल्ड नीड्स दिस डेफिनेटली। काम करते हैं, कुछ करते हैं अभी ना, थोड़ा सा टाइम पास, चेस खेलते हैं। आई एम नॉट गुड एट चेस, आई एम नॉट गुड एट चेस, but I'll still play as an intermediate because I'm decently good at chess. I'm not that bad. We'll see. We'll see. Okay, e4, e5. A lot of players are playing this period opening. Okay, we can transpose it into a scotch. If it takes, I takes, I again take. I don't know. If anyone knows better chess, please teach me. I would do this. Will he resign on me? Why the fuck has he disconnected? That's so annoying. Let's play the game. What the fuck? I don't know. Okay, okay, he's back. He's back. Now he has blocked this path. Can we capture this space? Nah, I just develop. Slow. Slow game. Okay. Now this is possible, right? Am I wrong? No, this is not possible. Okay. Using this. Also just castle. It takes. Hmm. Give do this with castle. Do this with castle. We have an open rook, and we play from there. Play from there. Nah, Beauty and the Beats doesn't work. You can try something like uh nah, that's too bad. Beauty and the Beats. That works better. Let's see. Oh, but I'll have an isolated pawn at the end of this. It's taking too much time. Too much time. Should lose. We should lose. Come on, make a move. Bro, he's so annoying. King G8? No, it's his move. पहले मूव में कैसल कर लिया था उसने. It's his move, and he has 40 seconds on the clock. Is he gonna play or what? अरे किंग G8 वहां होता है. अपना किंग G8 ले जाओ क्या? Fine. I guess ऐसे प्लेयर्स मिलेंगे अगर मैं. Let's just log in. Let's do puzzles. Let's do puzzles. Puzzles are good. And then we'll continue. Puzzle Rush Survival. Hmm. Hmm. Let's think about this. Takes. I do this. Let's checkmate. Hmm. Okay. Okay. Isn't there checkmate? कहता है पल पल. भी नहीं है. ये क्या है? मतलब अपनी छोटी पजल पे रुक रहा हूँ मैं. Is it about winning this pawn somehow? That doesn't work. If I do this, okay, he'll go here. Then I can take this. Can't just be winning about a pawn, right? 1 2 1 2 1 2. Can be. No, but we're down a knight. We are down a knight. This weird is so weird. This puzzle is so weird. What am I missing? I don't know. I don't know what the answer for that puzzle was, but that's somehow that's checkmate. This is easy. This must be easy. Boom, boom. If I do this, that's just checkmate, right? Um, then okay. Hmm. Black to move and win. Yes. Boom, boom. That's checkmate. He took something, but he missed checkmate. Where should I go? This is a night trapped. Doesn't look trapped. This is not trapped. You have to pick up these pawns. No, he can just reach there. You have to pick up this pawn. Why would I be so desperate to pick this pawn? Hmm. I can also give this check, but what's the point? I just. What the fuck? What's wrong? Let's see. Don't blunder that. I can take this. There's a checkmate. I can do this. Or this. Oh, this looks nasty. Maybe this. Then I do this. Oh, that's sick. Boom. Free coin. Yeah, sacrifice. These 665. नहीं जाना प्यार किया तो निभाना प्यार किया तो निभाना. That's did that too fast. What the hell? मैंने सिगारा कर दिया. Fine. That. This is working. This is what we have. These are the graphs that we made. Now let's get to the second part of the video. Close this. Close this. No need for that. Or that, or that, or that. That. Yep. Colab. You know. Right. Upload. It's fine. Just look. Unconventional. Big words. So we are not gonna change anything here. We are not. We don't want to interfere with any of this. You have to find the neural network correctly. We don't want to play around with all of that stupidity. Instead, what I was thinking was, so I have explained you how we are gonna train this, right? That explanation part is done. So we are gonna introduce new dense layers that are gonna convert this directly to the expected output, and we'll be able to train that to get a better network. Right? That's what we have discussed so far. I've explained this before. What are we using? We are using extra dense layers to convert this initial to first train the first layer, then freeze these weights, pass the first layer's output to the second layer. Now train the second layer using another dense network. Now, after that has been trained, now we pass the output of second layer to the third layer, and the third layer is learned in the conventional way as it is the final layer. It uses a dense layer already. This is the dense layer. Right. Now, we understand all of that. How do we change this code to make it susceptible to the new method that we are talking about? So we'll have to first of all introduce new dense layers. So this was the final dense layer. Let's refactor our code a bit. Final dense. This is the final dense. One more thing I want to add is that let's introduce a new concept called step. Right. So that's right. Do we need anything else? Do we need to pass this through the ResNet as well? Is my question. Should we treat ResNet as individual layers? We should, right? We should, ideally. Or we can conduct two experiments to see how the introduction of these concepts changes the overall layer. So if step is equal to 0, for the first step we are just training the first layer. So x is equal to self.pool self dot res1 self dot con1 x. Right. And we'll not be using any dropout layers for the reasons I explained before. I don't want to use any dropout layer in this method. And I'll also do something that x is equal to this and self dot dense 1 x. Final length remains the same for each of it. Dense 1. So what is dense 1? So dense 1 is defined here. Linear. Between 16 into 16 into 32. 16 into 16 into 32. Comma 10. That's our dense 1. So that's what we are going to return. Now, if step is equal to 0, 1. तो स्टेप इज इक्वल टू 0 तो वो यहीं पे रिटर्न कर देगा, नहीं तो वो आगे बढ़ेगा और x को बोलेगा self dot pool self dot res 2 self dot conf 2 x. अगर स्टेप इज इक्वल टू 1 होगा तो रिटर्न self dot final act self dot dense 3 x. नहीं तो अब वो इससे पास करेगा और इफ स्टेप इक्वल टू 2 रिटर्न जरूरत ही नहीं है. तो ट्रेनिंग के समय वी हैव टू एक्सप्लिसिटली डिफाइन दिस dense 2. नहीं तो वो और आगे पास करेगा एंड व्यू हमें चेंज करना होगा हर एक के लिए. That's the thing. That's something we'll have to repeat. So this should work. We can train this without steps or we can train this with steps. So let's also define the dense 2. Dense 2 is equal to n dot linear and let's make this even more clear. Find it like this. Now this network that we have made right now doesn't completely utilizes the concept we were talking about, right? That makes sense because अभी हमने क्या करा है, अभी हमने सिर्फ मतलब रेस ब्लॉक को अलग लेयर की तरह ट्रीट नहीं करा है. विल टेस्ट इट वन मोर टाइम ट्रीटिंग रेस लेयर्स एज अदर ब्लॉक्स टू सो दैट वी कैन सी कि इस कॉन्सेप्ट को हम जितना ज़्यादा इंट्रोड्यूस करते हैं इसका इम्पैक्ट क्वांटिटेटिवली कितना है. क्वालिटेटिवली तो इम्पैक्ट पता लग ही जाएगा बट क्वांटिटेटिवली इम्पैक्ट कितना है. सो उसके लिए हम लोग ऐसे करने वाले हैं. सो ट्रेन ओनली फर्स्ट, train only second, ये पूरे से ही पास होगा ना? हाँ बस सही है, और क्या। दिस इज व्हाट वी मस्ट नीड। सो हो जाना चाहिए। Let's test this for each one of them. My step is equal to 0. Step is equal to 1. Step is equal to not defined. Yep, it works. Now we need to define our training. Yep, that's right. That will work the same way. We have made it like that. And now talking about this, how do we change this? Okay, for epoch and range epoch. Range is equal to ये. So पहले के लिए epochs ये तो करना ही पड़ेगा ना, यहाँ पे है तो मॉडल कमा स्टेप इक्वल टू 0 रहेगा पहले, फिर 1 होगा, फिर कुछ भी नहीं होगा. उसके लिए 2 लिख रहा हूँ तो भी बस सेम ही रहेगा. That's good. So we can do steps is equal. यार नहीं, ऐसे नहीं करना. Not do it like that. Okay, let's keep it like that. Keep this like that. And when we are talking about this one, instead of doing it like that, ये हो गया. epochs के लिए ही ट्रेन करना है. डोंट इवन वांट टू चेंज द epochs गाइस, दैट्स इंपॉर्टेंट. बिकॉज अगर मैं epochs पढ़ाऊंगा तो टाइम ज़्यादा लग सकता है. बिकॉज ऐसा नहीं है कि मैं हर एक लेयर को उतनी epochs के लिए ट्रेन करूंगा, बट मैं लेयर्स को कम कम epochs के लिए यूज़ करूंगा. दैट्स वाई ये कम टाइम लेगा. या दैट्स द होल कॉन्सेप्ट. सो पहले वाला कितना टाइम ले रहा था, वी हैव दैट सेव्ड. दैट्स 251 seconds, right? So let's see how much time is this gonna take. If epoch is less than it's getting too tricky. Wait, need to think about this. How are we gonna implement this? पहले मैं सिर्फ एक लेयर को ट्रेन करना चाहता हूँ. So for epoch in range epochs, first step in range Shut. Right. It should work. And that's it. That was easy. Unexpectedly. I have not done it. So we'll see it through the graph. I've tested it once. You should see this working through the graph. It looked like it looked like let's do it. Ah, parameters. What is wrong? Parameters. Oh, dude. Oh, dude. Okay, let's try this again. So we know for sure that is working. That's good to know. So after 30,000 shares, this should set the parameters. False. Than that. Bro. No, bro. Nah, bro. Nah. This is working. That's good. There is that jump. Now it is reducing it. The parameters must have been set to false. That's the ideal case. I can optimize this program. You could have also written, nah, that would have been tricky. This is a good way of writing this. And the learning rate seems too slow for this network. Can learning rate is too slow. Not able to change anything. Okay, so see, it takes less time for sure. It took what? That was 51. So it took 30 seconds less. How much is that? 251. That's divide by what was it? 251. 27 by 224. 7 divided by 224 into 100. Yep, that's 12% faster. It's 12% fast. That's pretty fast. Oh, sorry. Why would I do it like that? I would have to do it like that, right? That's around 11% faster. The accuracy seems to have gone down. That is faster. How can we handle this accuracy problem? Let's see. Okay, nah, that's so accurate, right? Let's see how the training loss looks like. What shape? 10 1 10 5. What should I do? 10 5 minus chat, minus chat. That's a days. What? Oh, minus chat. Should be the same. Thank God, are you kidding me, bro? Oh, wow. That's not how it works. Let's try. Plus try plus 1. Oh my god. Right. Hmm. Now this is interesting. So this is how it is. But something that I don't understand is I don't understand why. Let's check our implementation from zero. There should be no error in this. It should be exactly how we want it to train. Otherwise, we'll be in problem. Hmm. Let's see. So here is where we have defined this. Con block, rest block are defined the same way. Initialization is same way. Forward, the steps are zero. First, pass the pooling residual network link up convolution. And for this one, and for this one, step is equal to zero. We pass it through the first convolution layer, resolution layer, then pooling layer. Then we train the first layer by directly giving it the result. Final activation through the dense one. Then we pass through this one as this doesn't get activated. If step is equal to 2, we do this, and do this. This seems right, right? We can follow this. Now let's come to the training part. This is also right. Validation loss. Is the validation always calculating like this? Oh, no. Validation should also get the step. On the step. Validation should also get the step. That's what's wrong here. No, not. You should also get the step. That's how it will calculate, right? Um, One mistake has been found. Let's try to look for another mistakes. Step is 3. Epoch divide by 3. Image is equal to A. Labels is equal to A. One more thing I was curious about was why is there any difference in these? No, they are training till 10,000, right? That's cool. 0, 201, 201, 201, 50. Yeah, that's true. So here. Let's see. So if steps in range 3, image comma labels is equal to next iterate train. We got the image, we got the labels. If step is greater than 0 for parameters, we set its parameters to false. All of these parameters to false. If step is greater than 1, we set all of these parameters to false. And these are also false for 2. Right. Then output is equal to model images comma step. First one for the one, two for last one. If that one के लिए it will stop training that and go to the output model के लिए will stop training that, go through there, pass on through those networks the exact same way without there being a requires grad. We are always doing optimizer at 0 grad. Optimizer has all the parameters, so that is also correct. Yeah, this all should be correct. And let's not change anything. Let's just change that. Val loss. Okay, this seems right. Only changes to the well load. That makes sense, right? So that's why it's reducing so quickly after that, and it's not reducing before. That's how it is training. But there is one more problem if we can fix that. Right, maybe we can upgrade this even more by not just passing the outputs like that, but taking the average, maybe slowly increasing it. No, but this makes sense to me like this. No, no, no. So, it from making sense to me. And yeah, one more thing. As there are less chances of overfitting, we can increase the learning rate. Let's do that. Is maybe 5 instances. That's a better risk. Finish so quickly. Just like that. You already reached 70% loss. Boom. Oh my god, are you kidding me? Oh my god, this is amazing. Just look at the results. Loss is tanking down. Wow. That speed? That's unexpected. This behavior, I also didn't expect this behavior. We have reached our maximum loss. Wow. So this layer really has learned something this time. Now let's see what the second layer improves on this. How much can the second layer improve on the first layer? Because it makes sense now. Now they should just improve on the previous layers. Let's see. Okay, okay, still there. Okay, we're along those lines. Wow. See, here is 75% accuracy, 76%. Oh, it is slowly tanking away. That's jumping is set is that's okay. On average, we are getting 0.26, and that's 74% accuracy. That is better than before. 73% accuracy on average, I guess. Wow, man. Now it should improve further. Now it should improve further. See how much it can improve. How much can the last layer improve on the previous layers? That learning rate parameter is an important one. That's what we have discovered. Learning rate can be higher because it's possible. Train the network. 20 That's the discovery. Let's see. 0.244 and the time. Oh my god. Victory pose. We have actually, you can see our validation loss is lower than the training loss, and that's because we are training on all different iterations. So this is amazing. So we have improved on our accuracy. Now we have 76% accuracy. That's higher than before. And now we also have a much faster training loop. So accuracy question mark is not a question mark again. Accuracy is also improved on unseen data, making the model generalize better to new data. Which means that our new training loop allows the model to generalize better. This would complement our idea of neuroplasticity, that each layer added should improve on the previous layer. I mean, Paisa, this is this is actually an amazing result if you think about it. So okay, we are using 218 seconds. वो पिछली बार ज़्यादा seconds इसलिए लग रहे थे क्योंकि हम validation loss में steps नहीं दे रहे थे. So we have saved even more. We have saved what? 31 seconds. So we have saved. My God, are you kidding me? We have taken 12.3% of time. We are making the whole training 12.3% faster. We have improved our accuracy from 73 to 76. So that's 3 divided by 72 into 100. 73 by 100. What the fuck am I doing? I've gone crazy. Okay. That's 4% increase in the accuracy. And other than that, now when I plot the graph, okay, let's see the results first. Okay, so okay, they don't seem much correct. What is it? Yeah, okay, so I'm doing this right? I'm not sure. Let's see. So see, the graph is much more interpretable. How? We can see what minima has each layer produced. And this result somehow shows me that maybe the second layer is not working very well. Maybe if instead of using the second layer, I directly put the input to the third layer, with the only difference being the channels each layer has, maybe that will produce better results, as the second layer doesn't seem to have affected the network much. So that's the whole point, right? That's the whole point. We are able to interpret so much better. Yes, the result seems much more consistent. These validation roses. I'm correct at calculating this, right? I'm not calculating this wrong. This is not this, there is no stupid mistake in this, right? Nope, there is no stupid mistake. Let's try this one more time. I don't know why is there slight error in this. So yeah, this one is correct. This one is not correct. We still are at 76% accuracy. It is not the best accuracy in the world, but again, the network has better. Yep. So this is good. We have increased 12% in speed, 4% in accuracy, and the network is so much more interpretable. When you look at this graph, these graphs represent much more. They tell us about each of the layer, how each of the layer has learned, we can see that okay, the first layer overfitted the data here. We can clearly see that because the validation loss, it became even lower than the validation loss. So we can interpret each layer individually much better. There is and so all of these three benefits. Accuracy, I was uncertain about. I was not sure that it will be more accurate than before, because it might be equally accurate or even slightly lower, because we are training each layers and we are putting some restrictions into the network. But again, as we can see the results, 0.24, 0.25, 0.26, 0.25, 0.23. So I guess on average this corresponds to a 76% accuracy, which is much higher than our previous 73% accuracy. Now, as again, it doesn't sound much higher, but it is 2% improvement without doing anything. And we are using the same number of epochs and we are using less time. The most important thing, we are using 12% less time. Now it doesn't seem much significant, but understand this: if you are training a neural network for say 2 hours, right, 2 hours 120 minutes, now you will be saving 12% on this. That will make it around 1 hour 45 minutes. It's saving you 45 minutes. And when we talk about neural networks in the context they are being trained right now, where they have to be trained for 4 days. Now if you are saving 10% on 4 days, you are saving 1/10 of a day, 4/10 of a day. That's much faster. It's way faster. So yep. We know this model works now. Definitely works. Yeah, there's still so much. But why are there still so much error one there? Okay, that's this is also an advantage, right? We have trained such a big neural network and we have steps too. So if I see that the second step might be causing too much errors, okay, let's test the neural network too. Because by creating this neural networks, somehow we have also made 3 neural networks in the progress, right? Now we have 3 different neural networks. So again, I can do this and I can see the results for this. See, the second network seems to produce some good results. Maybe better than the third layer. So maybe the third layer can be discarded. But yeah, this is the kind of interpretability I am talking about. While in the process of making a neural network, we have created three different neural networks. We have a completely interpretable graph of these three neural networks that can help us improve, optimize our hyperparameters, architecture, create a better neural architecture, because we have all this data that was not there before. We have all this layer wise data that was not there before. See, let's compare the two graphs, right? Okay, where are the previous graphs? Well, oh my god, this is so good. Oh my god, this is good. This I did not expect. Where is it? Okay, let's upload it. Stupid Google Colab. I hate Google Colab. Have I said this? I might have said this, but I hate it. Okay, I don't know the current standards, but let's compare it to an article. Okay, this is an article on machine learning mastery. They have created three different neural networks. One of their network produced an accuracy of what? So the 67%. Then there was another one with the accuracy of 71, and then there was another one with the accuracy of 73. So when we were making our previous network, we were able to achieve an accuracy of 72%, which I said is less than this because we haven't hyperparameter optimized, which is needed if you want to stick to your data set. But instead, when we train this with a different training loop without any hyperparameter optimization, and this reduced the training time, and now our current accuracy is 76%. So if we compare it with this article, we have achieved a higher accuracy than this, and they have used the standard training loop, and their loop is hyperparameter optimized. So yeah, that's the thing. And you can see VGG is a standard block. VGG networks are very standard. So these are the kind of blocks we are also using. But yeah, so अभी के standards के हिसाब से जो placement है, I'll say it is better, right? Somewhat. We are using the same network, approximately the same network. Obviously, they have used some parameterization tricks. तो नहीं, हाइपर पैरामीटर का काम ऐसा है ना कि जैसे जो मैंने अभी ये नंबर्स दिए, अभी मैंने ये नंबर रैंडमली अपनी मर्जी से सेलेक्ट करे, राइट? जैसे ये बैच साइज मैंने एज अ नंबर दिया, ये लर्निंग रेट मैंने एज अ नंबर दिया, ये काफ़ी ज़्यादा मैंने अपनी मर्जी से और थोड़ा बहुत हिट एंड ट्रायल से दिए. बट इसमें क्या है, मैं कह रहा हूँ कि हाइपर पैरामीटर ऑप्टिमाइजेशन जो है वो पैरेलल में चलता रहेगा. अभी जो ये वाला है, मेरा जो ये वाला ट्रेनिंग पैरामीटर है, इसके अंदर भी अगर मैं हाइपर पैरामीटर्स को ऑप्टिमाइज करने लगता हूँ हिट एंड ट्रायल कर करके कि किस नंबर को मुझे क्या करना चाहिए, जो मैंने अभी रैंडमली नंबर सेट करें अपने हिसाब से, मैंने एवरेज पूल अपने हिसाब से यूज़ करा है, मे बी मैक्स पूल बेटर रिजल्ट दे, तो ऐसे ऐसे हाइपर पैरामीटर्स को अगर मैं ऑप्टिमाइज करता हूँ तो इसकी एक्यूरेसी भी और बढ़ जाएगी. तो वो पैरेलल रिसर्च है, वो अभी भी कर सकते हैं. बट इसने सिर्फ हाइपर पैरामीटर वगैरह कुछ भी ना चेंज करके सिर्फ इसे इंप्रूव कर दिया. अब इसके ऊपर अगर हम फर्दर हाइपर पैरामीटर ऑप्टिमाइज करें तो वो और बेटर हो जाएगा. तो वो चीज़ अभी भी वैलिड है. दैट्स द पॉइंट कि वो पैरेलल रिसर्च है कंप्लीटली. उसमें मैं डिवेल नहीं कर रहा, उसमें टाइम वेस्ट नहीं कर रहा क्योंकि ज़रूरत नहीं है, वो इस पर भी करा जा सकता है. बट दिस इन पैरेलल इम्प्रूव द नेटवर्क विदाउट वी डूइंग एनीथिंग. एंड हाँ, स्पीड में बहुत डिफरेंस है यार. 10-12% का डिफरेंस बहुत बड़ा डिफरेंस है. हम्म. और ग्राफ भी दिख ही रहा है, और लर्निंग रेट भी कम हो गया. अगेन वन मोर थिंग, जो पहले हमें लर्निंग रेट यूज करना पड़ रहा था, जो हमने हिट एंड ट्रायल कर करके देखा, 1e-7 का करा था. मतलब हमने 1e-7 का मतलब हो गया 10⁻⁻7 के अराउंड का लर्निंग रेट था. बट अब हम 5e-6 यूज कर रहे हैं 10⁻⁻6 के अराउंड. तो होगा क्या, जो ओवरऑल मेरे 10,000 इटरेशंस के लिए मुझे इसे रन करना पड़ा था ना, वो मैंने इसलिए चेंज नहीं करा क्योंकि मैं टाइम पर इटरेशन देखना चाह रहा था कि उतनी ही इटरेशंस के लिए कितना टाइम रिड्यूस होता है. बट अगेन लर्निंग रेट इस वाले मेथड में बढ़ाया जा सकता है, और ये इतना बाउंस नहीं हो रहा, ये स्टिल काफ़ी कंसिस्टेंट है इतने हाई लर्निंग रेट के बावजूद. तो इसको मैं इपोक्स को मतलब ओवरऑल इपोक्स को भी घटा सकता हूँ, इसको भी मैं मे बी मतलब अगर 6 इसको भी कम करूंगा तो टाइम ये बहुत ज़्यादा घट जाएगा। तो टाइम में सिर्फ 10% इंक्रीज नहीं है, 10% तो स्ट्रेट फॉरवर्ड इंक्रीज डिक्रीज है, बट लर्निंग रेट इतना फास्ट हो गया है कंपैरेटिवली कि अब मैं और कम इपोक्स में उतनी ही चीज़ें सीख जाऊंगा, इतने इपोक्स चाहिए ही नहीं, क्योंकि देखिए ये 0.24 वाला जो कंसिस्टेंस है ये बहुत पहले स्टार्ट हो गया था, ऐसा नहीं है। और यहाँ पे ही आने लग गया था 0.24 0.26 वगैरह आधे इपोक्स में, तो मैं उससे आधे के लिए ट्रेन कर सकता हूँ। सो टाइम में तो एक्सट्रीम लेवल इम्प्रूवमेंट है, टाइम ही मेन फंडा था और टाइम तो गजब। ओ भाई हाँ, तो let's open this and now we have done this. Okay, that was a lot of progress. ओ भाई साहब, अब लिखना है रिसर्च पेपर। आई हेट दिस, आई हेट दिस। हेलो, मोम इन द चैट, मोम इन द चैट से नमस्ते शशांक। शशांक, गुड गुड, नमस्ते। तो तो yep, दिस इज वर्किंग मच बेटर। तो जो हाँ, तो अब ये सब तो हो गया। अब ग्राउंड जीरो पे आ गए दोबारा, अब रिसर्च पेपर लिखना है। दिस इज वर्किंग, द मॉडल इज डेफिनेटली वर्किंग, बहुत फास्टर है पहले से। वही अगेन ऑल ऑफ द रिजल्ट्स जिसकी बात कर रही थी, जो एक्सपेक्टेड रिजल्ट्स थे, एक्यूरेसी हैज़ बीन इम्प्रूव्ड, जनरलाइजेशन हैज़ बीन इम्प्रूव्ड, ओवरफिटिंग की ज़रूरत नहीं है, ड्रॉप आउट लेयर्स की ज़रूरत नहीं है। इसके बाद कॉम्पिटेशनल फास्टर है, काफ़ी फास्टर है, लर्निंग रेट भी कैन हैंडल larger learning rates. That's the point. So epochs, नहीं लिखते हैं, so epochs can be set to even lower, allowing even faster learning. That's the concept. Now, accuracy is also improved on NC data, more interpretable neural network. Also, by training a neural network, you have in the process made 3 different neural networks that you can experiment with. What layers discard if necessary. In different neural network, each layer. ये सब ये सब साजिश क्यों हो रही है मेरे खिलाफ? मेरे खिलाफ कोई साजिश नहीं सहूंगा मैं। ये मेरा लंच है मेरे पास, मैं अपना लंच खा रहा हूँ तब से। हम्म, ये यही है लंच, यही है लंच। Namaste, namaste. Okay, so after all of this, we know it is working, but how much does it work? तो हमारे पास क्वालिटेटिव रिजल्ट्स हैं, क्वालिटेटिव एडवांटेजेस, but what we need to experiment with now is quantitative advantages, results, impact, quantitative impact. तो पहली लेयर में हमने रेजनेट और कॉन्फ को एक लेयर की तरह ट्रीट करा था। अभी तक ये सब कर लिया, तो पुराने वाले का ना ऐसे डिलीट करो। ये रहा, ये भी हो चुका है। तो सबसे पहले एक बेसिक नेटवर्क बनाया, इसके ऊपर टेस्ट करे, फिर इसके टेस्ट रिजल्ट्स आए अपने पास, फिर उसको डॉक्यूमेंट करा, पहले वाले के रिजल्ट्स कैसे थे। उसके बाद इसको हमने नए वाले को ट्रेन करा, जो अनकन्वेंशनल है, जो मेरा मेथड है। फिर उसके रिजल्ट्स इवेल्युएट करे, उसमें चेंजेस करे, और फिर उसके रिजल्ट्स ऐसे आए, एंड ये रिजल्ट्स बेटर हैं। तो ये रिजल्ट्स तो बेटर हैं। अब एक्सपेरिमेंट करना है कि स्टेप्स और बढ़ा दें तो क्या होगा अगर हर एक लेयर को ऐसे ही इंडिविजुअली ट्रेन करा जाए। क्योंकि अभी अभी क्या कर रहे हैं ना हम लोग, अभी दो लेयर के ग्रुप में ट्रेन कर रहे हैं, एक कॉन्व लेयर और एक रेज लेयर एक साथ ट्रेन होती है। एक कॉन्व लेयर और एक ट्रेन लेयर एक साथ ट्रेन होती है ना। तो अभी हम क्या करेंगे, स्टेप्स को और बढ़ा देंगे और इनको हर एक को इंडिविजुअली ट्रेन करेंगे। एक सबसे पहले सिर्फ एक कॉन्व लेयर ट्रेन होगी, फिर एक रेज लेयर ट्रेन होगी। अभी के लिए एक कॉन्व एक रेज लेयर एज अ ग्रुप ट्रेन होता है, फिर अलग कॉन्व और रेज लेयर एक ऐसा ग्रुप ट्रेन होता है, फिर एक अलग कॉन्व और रेज लेयर एज अ ग्रुप ट्रेन होता है। इसके बाद हम लोग ऐसा करेंगे कि हर एक उसको भी फर्दर सेगमेंट करके उसको भी स्टेप्स में डिवाइड करेंगे, और हर एक कॉन्व लेयर अपने एक कॉन्व लेयर फिर एक रेज लेयर एक कॉन्व लेयर। तो टोटल स्टेप्स जो अभी के लिए 3 स्टेप्स थे कि एक बार सिर्फ पहली कॉन्वलेयर से आउटपुट चला जाए, जो अगर वही वाला डायग्राम देखें कि हिडन लेयर हिडन लेयर हिडन लेयर आउटपुट लेयर, तो अभी डायरेक्टली यहाँ से यहाँ आउटपुट जा रहा था, फिर ऐसे पास होके यहाँ से आउटपुट जा रहा था, फिर तीनों से एक बारी में आउटपुट जा रहा था। अब उसको भी फर्दर सेगमेंट कर दिया, अब टोटल हमारे पास ऐसे 6 हो गए, और उन 6 में अब पहले वाले से जाएगा, फिर पहले दूसरे से पास होके जाएगा, फिर पहले दूसरे तीसरे से पास होके जाएगा, फिर पहले दूसरे तीसरे चौथे से पास होके जाएगा, पहले दूसरे तीसरे चौथे पांचवें से पास होके जाएगा, फिर फाइनली लास्ट में वो एकदम लीनियर 6 से जाएगा। तो उससे हम लोग इवेल्युएट करेंगे कि क्वांटिटेटिवली कितना इम्पैक्ट आ रहा है इस आइडिया को इम्प्लीमेंट करने का किसी भी न्यूरल नेटवर्क के अंदर। अभी हमने क्वालिटेटिव रिजल्ट देख लिया कि हाँ डेफिनेटली ये टाइम को इम्प्रूव कर रहा है, एक्यूरेसी को इम्प्रूव कर रहा है, और भी चीज़ों को इम्प्रूव कर रहा है। तो अब हम लिखते हैं उसके लिए कोड। अनकन्वेंशनल क्लासिफायर 1